Hi guys, thanks for joining our course on the introduction of mud crab farming using vertical farming methods. My name is Yit and I will be your instructor for the course. My background is mainly in engineering, in chemical, mechanical and as well as petroleum. I've worked in oil and gas industries and now have chosen a full-time career in aquaculture. We run a farm in Malaysia and we have taught over 140 students year to date. So we are glad that you have made an effort to enroll in this course due to popular demand for an online platform. And hence we have recorded most of our sessions here on Udemy. So without further ado, I would like to start the main bulk of our lectures. So the goals of using RAS for aquaculture systems is to achieve what we aim for, which is indoor productions. So RAS is a short form for recirculating aquaculture systems. The goal here is to produce more fish using less water and have more control over production. One of the major benefits of utilizing RAS for an indoor aquaculture production system is to achieve temperature control and to ensure biosecurity, isolating your products from infectious diseases and dangerous. RAS system has been practiced in many countries, mainly in the US as well as Norway, where they are used to farm high-value species such as rainbow trouts and the Atlantic sturgeon. So, how do we define a recirculating aquaculture system? By definition, an aquaculture production system that recycles and renovates the water for the culture of an aquatic organism. A simple way to define the amount of recirculation rate is a 95% recirculation rate. In other words, you indeed have to carry out some form of water change, and which can be up to 5 to 10%. Some useful conversions, so 1 meter cube of water is actually equivalent to 1000 liters, which is also 1000 kilos.
Note that the recirculation rate for any RAS system is anywhere between 30 minutes to 1 hour.
So for RAS systems, one favorite common question I get from individuals is, how often do you exchange water? So I would say 0 to 20% is the typical rate of the volumetric exchange per day. Typically, it is very difficult to run at 0% water change, which also means that you do not change the water for a long time. Commercially, we have seen the lowest to be 3%, and we are running about 7 to 10% every day. It is not that we intentionally change out the water, but instead you sometimes lose water from the backwashing of the filters. So it is by operating the filters that you do lose water, irregardless of the filtration media that you'll be using. So factoring into leaks that is definitely going to happen in your aquaculture systems, sometimes that could account up to 9 to 10% of a volumetric losses during the backwash and leaks. And when you lose water in the aquaculture systems, you do have to replace them. So I would say a 9 to 10% is a conservative amount. So what are the pros of using recirculating systems? So I would first highlight the cons, especially pertaining to the mud crab industry. Number one, you definitely reduce the water requirements required for the mud crab aquaculture. You will be also farming them in a very intense manner, in a way that you will be stacking them vertically in boxes, and they are spread out over a very small floor area. Improved water quality can be true or false depending on your knowledge of operating a recirculating system. Waste capture, better feed conversion, and the isolation of products have also been known as pros for recirculating systems. We have also seen better inventory control when you are utilizing what we call recirculating systems with vertical farming, which we will explain in depth later on. However, there are also cons of using these systems for mud crab aquaculture. Number one is that it requires a high initial investment. It took us about $20,000 to get everything set up, and that includes of all transportational costs of equipment up to our doorstep, as well as the required civil works. On top of that, you also running an aquaculture plant will also result in a very short response time. What do we mean by short response time? It is the reaction time available for you to carry out any corrective action in the presence of an emergency, may it be power failure or some other form of emergency. As the RAS system is a life support for all of the creatures inside, a failure, for example, like the pump, would always have a catastrophic result. Also, there have also been a lot of failures in using RAS systems. Another point of cons in using RAS system is the required economy of scale, as most systems will yield the benefit of having a volume. For example, in the soft-shell crab business, which also utilizes the same technology as, usually you would require scale of a minimum 5,000 boxes to be economical. Lastly, a lot of people profess to be experts, but they are usually not. So our advice from RAS Aquaculture is to weigh and judge every advice you receive with a pinch of salt and use your fundamentals to understand whether it is logical or not. How are recirculating systems used currently? So common uses for RAS systems are in the hatchery business, nursery, quarantine, fingerling production, purging of market-sized products. So what do you mean by purging? Purging of market-sized products could be anything between restaurant chains, aquariums that are located in restaurant chains that often purge the creature, whereas be crabs or shrimp, of their ammonia in their system, ensuring a better quality growing out system. A near market holding system is also possible to utilize with RAS. So what are the common uses of RAS systems in the crab business? So we have previously seen that restaurants always like to store their crabs in the aquarium, so which is what we call purging of market-sized products, and near market-sized holding systems. So holding systems can be run on RAS systems, which increases the shelf lives of the crabs. And lastly, it also has been used for crab fattening and soft-shell crab, and also in some part of the world, grow-out operations. The RAS system is always designed based on how much you are feeding and not how much you are stocking. So do not be impressed by those who have claimed that their system is up to 1,000 crabs or 2,000 crabs. Be impressed if they can feed the crab to 3 to 5% body weight while still maintaining good water quality. Based on material balance, we know that for every kilo of feed we will be providing into the system, it requires 0.25 to 1 kilos of oxygen to process, and it also requires what we call alkalinity. It requires 0.18 to 0.4 kilos of alkalinity, and as a byproduct we produce 0.35 to 1.4 kilos of carbon dioxide, and we also produce waste, which is feces and uneaten feed, and most importantly we produce ammonia, in total ammonia nitrogen. And this is all from processing only 1 kilo of feed. Your RAS system design have to consider the 6 following points. Number 1, you have to worry about bacteria. So bacteria can be pathogens in general, alright? And your system has to remove waste efficiently, and it has to convert ammonia to NO2 to NO3, and it has to remove CO2 while maintaining alkalinity and pH and adding oxygen. These 6 points are general for any systems. However, for crabs, we only have to worry about the 4, which is pathogens in the form of bacteria and viruses, removing solid waste, converting ammonia to NO2 to NO3, while maintaining alkalinity and pH. This is the different unit processes that is typically found in the aquaculture systems for fish. We start off with the fish tanks, in which the fish are cultured in a circular tank, after which the water will flow through what we call a drum filter, which is what we call mechanical filtration, and it will then be disinfected with UV light and remove ammonia using the biofiltration process. And lastly, it will go on to ozonation, which is also a form of disinfection and remove additional organic compounds. And lastly, we will remove CO2 from the system, adding in back oxygen and flowing it back to fish tanks. So these are the typical operations that you would see if you're visiting a salmon farm per se, trout farm, or maybe a sturgeon farm. Luckily for us, we utilize a simpler process flow diagram. Firstly, on the leftmost side, we have what we call the culture tanks, and these are the individual boxes in which the crabs are grown in. Followed by solid removal, which is the utilization of media filters to remove away any solids made that is resulting from feed or feces. The third part will be removal of ammonia, NO2 and NO3 using the biofiltration process, followed by disinfection. Since crabs can tolerate high CO2 and low oxygen levels, the water after disinfection will be recirculated back to the culture tanks and recycled. So that's all for now. In the next lecture, we will show you the importance of solid removal in the culture tanks and the solid removals in the media filter and different technologies that are employed for solid removal. So see you then. Hi guys, thanks again for joining our course on the introduction of mud crab aquaculture with vertical farming. In the previous lecture, we have shown you how RAS systems are being used in the mud crab aquaculture and what are the individual pros and cons and the strict definition of recirculating aquaculture systems and the daily exchange rate. In this lecture, we will now then explore the solid removal strategies which occur in the culture tanks, followed by solid removal strategies that are being removed via mechanical filtration. Firstly, we need to understand the different types of solid that we are trying to remove water. The first type of solids are what we call as settable solids. Settable solids are defined as solids that will settle to the bottom of the water column within 1 hour. On the other hand, suspended solids refer to small solid particles which usually remain in suspension of water. In this lecture, we will be focusing on removing settable solids. In RAS systems that are being designed for fish are usually cultured in circular tanks, and uneaten feed and feces usually constitute to what we call as settable solids. In the fish aquaculture industry, they always utilize circular tanks with a diameter to depth ratio of 3:1. A large diameter to depth ratio would often mean that the tanks are very wide and very shallow. This often results in solids accumulating at the bottom of the tank. As the cleaning action is usually achieved by primary rotating flow, which forms a vortex, and by secondary radial flow, which is in the form of a teacup effect. Combining these two methods of cleaning actions, susceptible solids such as feed and feces would not accumulate in the tank. It is important to remove the uneaten feed to ensure that it does not deteriorate the water quality and result in jeopardizing the health of the fishes. Typical hydraulic retention time in tanks are about an hour. There are several technologies to introduce water into the tanks. In the industry, it is common, like the picture on the left, to introduce water simply by an overlying pipe. However, this is not the most optimum way to ensure that you have a primary rotating flow. A better way is to utilize what we call a vertical manifold, which is on both pictures on the right, which can be constructed with PVC pipings. This is to ensure that water is being introduced into the tank in a uniform manner, promoting the formation of rotating flow, primary way to ensure a vortex is forming. To clean out the solids, the typical cleaning velocity you require is 15 to 20 cm per second. It is likely that if your flow introduced, if it's not high enough, will not result in the formation of vortex. However, the current introduced by the flow should not be exceeding the safe swimming velocity, which is defined as the formula, as it will result in excessive stress caused on the fish. So ideally, you would require to design a tank that can self-clean, but on the other hand, do not exceed the swimming velocity, and they have placed a considerable amount of effort in researching what is the optimum velocity. However, this is not the case for most of the vertical mud crab systems out there in the market. As you can see on the picture here, this is the boxes that we are currently using. It consists of a box along with an outlet tube to maintain the water level in the box. As you stack them up, this is how it looks like. So this is a picture of a crab after being fed with shrimp feed, which is a kind of formulated feed. Formulated feed tends to disintegrate in the water over time, resulting in a sedimentary layer onto the boxes. As you can see, cleaning out this shrimp feed is difficult, and it might incur a lot of operating costs to clean out this solid. There are other feed that you can consider using in your vertical crab farming business. For example, trash fish that is easier to clean out because they remain in bigger chunks after feeding. You can clean them out with nets. However, typically cleaning will take up 2 to 3 man-hours on a daily basis, and each box will require 45 seconds to 1 minute to clean. Note that we do not clean each individual boxes every day, and we only clean out those that are dirty or have some solids that have accumulated. Note that solids that are accumulated in your systems would often result in deteriorating water quality and often result in diseases. We will now show you the typical solid removal efficiency of the box that we are currently using. The box that we are using is made from China, which has a HDPE build, and it also uses an outlet tube to ensure a water level is maintained in the box. As you can see, once an outlet tube is used, most of the feed will accumulate at the bottom. The type of feed here in our demonstration is trash fish and shrimp feed. In both cases, we can see that the feed tends to accumulate at the bottom. Using a net, it might be easier to clean out the solids that are bigger in size, for example, the trash fish. However, for solids like the shrimp feed, it is relatively difficult to remove with a net. An easy way to remove shrimp feed is to remove the outlet tube, drain out all the water, hose it down or flush it with water to remove all of the solids. However, the difficulty is removing the outlet tube. As you might notice, the crabs are living in this enclosure. And to risk putting your hand in the boxes to remove the outlet tube can be sometimes quite difficult and time consuming. Many of my clients have approached us about making their own boxes. They're often talked about what sort of plastics to be used and what is the minimum space requirements. More than often, we find that people tend to overlook the importance of settable solid remover. To ensure your box to have a good removal system will incur a higher cost, or in other words, incorporating other features to remove settable solid would result in a more expensive box. However, you need to realize that by doing so, you can greatly reduce your operating costs. For countries with low labor cost requirement, for example, in Philippines, Indonesia, India, it might be economical for you to have a cheaper box while getting your staff to clean them out. However, for countries like Singapore, Australia, or even places like Hong Kong, where labor cost is very high, you might want to invest in a system that can remove the settable solid in a much more productive manner. There are many manufacturers for boxes out there in the market, and one of the important criteria we would like to emphasize again, apart from cost, building material, is to look at the settable solids. However, we have only strategically tested out the boxes which is from China, and we do not have any data to validate most of their claims. So that's lecture. In the next lecture, we will talk about what are the different strategies to remove suspended solids that are being passed through water. And we will see you soon. Hello everybody. We hope you enjoyed the previous lecture on the solid removal of settable solids. In the previous lecture, we've talked about different box design that could settable solids in a box and how inefficient designs could lead to excessive labor costs. In this lecture, we will now focus on the solid removal of suspended solids. So if you recall, suspended solids are solids that do not settle down within an hour. So in theory, these solids will be floating around the water, able to be removed from the box. So once they exit the box, we will then go through another process in which we call the mechanical filtrations. The technologies that are used for suspended solid removal often rely on what we call sieving, or in other words, mechanical filtration. Based on the particle size, we can break down the traditional filtrations into conventional particles filtrations, microfiltration, ultrafiltration, nanofiltration, and even reverse osmosis for very fine particles. The design criteria for any suspended solid remover is to have a range of the type of solids that you will be accumulating. Sometimes, if you have an incorrect diet formulation, it will cause the liquid feces to remain in the suspended solid form instead of a settable solid. And you would require a very fine mesh to sieve out all of these liquid feces. Technologies that are currently used to remove the suspended solids are very similar. They all utilize what we call a filter media to remove away the remaining suspended solid. One good example is this setup over here we have on the right, in which we have a beaker filled with liquid and suspended solid. As you pour them through a piece of filter paper, what you can get is the clear liquid. So traditionally, this is what we have been doing for the filtration process. There are several technologies that exist in the market to control suspended solids. The first being the most commonly drum filters. The second will be what we call the media filters, which are sand filters or any equivalent filters. And these are additional, not so common technologies like tube settler, cartridge filter. And lastly, we have what we call a foam fractionation. We will cover foam fractionation on a separate lecture because due to its unique characteristics. We will now look into the theory of applications for a drum filter. Drum filter is widely used in the RAS systems. The liquid is to be filtered and discharged by gravity into the drum. The perimeter of the drum is covered by a mesh, so impurities larger than the perforations are trapped inside of the surface while clean water will exit. The typical design criteria is to understand the pore size, the flux, the type of suspended solid size, and whether is it a freshwater or saltwater application. So what we have here, we can see here is how a typical drum filter looks like. As you can see, dirty water will enter the drum filter via the center, and the drum slowly rotates while the clean water is filtered out through this mesh. Any filter eventually will clog up over time. However, the drum filter has a continuous cleaning method, as the drum filters are backwashed with a high water spray using from the filtrate. So sometimes auto trigger can also be activated using water sample in the drum. So I will now show you a quick animation of how a drum filter looks like. Water will enter the drum filter in the middle, as explained earlier. As the drum rotates, it builds up what we call a filter cake. So this filter cake will accumulate on the side of the wall, while clean water will pass through the drum and being filtered. So firstly, it is important to control the pore size of the drum, as different pore size will give you different filtering capabilities as well as different flux. We earlier mentioned that drum filter has a continuous cleaning action, and it is achieved using so. As the filter cakes are being built up on the side and carried up vertically, water that is being filtered is used to backwash some of this filter cake buildup, and the filter cake will be removed as a slurry. So this is what we call a continuous cleaning process, where some of the water is being used to backwash and carrying out all the dirty solids. The first important part of the drum filter sizing is to understand this. A smaller pore size will give you a lower flux, and you have to probably backwash it. However, a larger pore size will give you a higher flux, but you are not able to filter small particles. So understanding of the type of solid that is expected in the system is important, as it will determine your pore size, which will give you the corresponding flux, and from there you will estimate how much filter you need. Drums in the aquaculture industry, especially in the fish industry in a saltwater process. However, do note that drum filter is usually more expensive as compared to the traditional media filter. There have been debates going on the benefits of using drum filter and the cons and using drum filters. One of the cons of using drum filters with formulated feed is sometimes formulated feed tends to disintegrate when they are rotating in the drum, and further aggravating your suspended solid issue. We will now move on to the next part, which is utilizing media filters for suspended solid treatment. Number one, it is definitely cheaper as opposed to drum filter. And the theory of operations is relatively simple, in which you pass the water through a packed bed media, which can be filled with sand. The way how you distribute the sand can be done in different manners. You could use the coarser sand at the bottom, followed by the medium sand and the finer sand on the top. Due to the pressure loss across the media filter, sometimes you will require a pump to pump the water through the media filter, which is unlike the drum filter, which accumulate at the top of the sand filter, and you will require a backwash to remove away the accumulated solids. In each sand filter, you require different sand size distribution for efficient backwashing and filtration. So in our case, we have shared with you the type of sand size distribution we are utilizing in our system. The sand filter volume is about 1.1 meter cube, and we are 72% of it is sand of 0.6 mm to 1.2 mm, and 12% of it is sands that have diameter from 1.2 mm to 2.4 mm. The largest type of sand distribution we have is from 2.4 mm to 4.8 mm, which accounts for about 16%. It is important to know how to design your sand size distribution. An easy way to do this is to go talk to your local water filtration manufacturers or water filtration systems designers that typically design your cartridge filter and your household sand filters to help size your sand accordingly. Alright, and it's also important not to use the fine sand for all of the sand filter, as when you tend to backwash, there is nothing to hold back the fine sand. In our case, the coarse sand is actually located at the bottom, followed by the medium and the fine sand at the top. Operating the sand filter would require some tricks and knowledge, as the sand filter is not like the drum filter in which it utilizes what we call a continuous cleaning. Suspended solids that are trapped inside the sand filter has to be removed from the system, and the removal method is to execute what we call backwashing. On a daily basis, we have to backwash at least once to ensure that the particulates that are trapped do not start decomposing into the system and further deteriorating your water supply. We do a backwash of at least 60 seconds to ensure all trapped particulates are removed. However, by doing backwash on a sand filter system, you usually tend to use system water to perform some sort of backwash, which for some of us can be quite costly, especially if you are located far from the coast. So one way of doing it is to change the piping, in which when you're about to backwash, you will swap the piping into a freshwater line and use freshwater to backwash. Because a backwash up to 60 seconds would sometimes reduce salt water by at least 500 to 1000 liters, and the salt needed to bring back to the original salinity will take 4 to 5 kilos. So depending on who you're buying the salt from, the cost can range up to $0.50 to $2. So that's all for suspended solid. In the next, foam fractionation, which is suspended solid as well as removing organics. Hello everyone, we hope that you have been enjoying our course on the introduction to mudcrab vertical farming. In the previous lecture, we have shown you how solid remover, mainly suspended solids, can be removed using drum filtration or media filtration. In this lecture, we will be covering a specific part of solid removal using what we call as foam fractionation. To recap, suspended solids are solids that do not settle in the column under an hour. So these solids will remain as fine particles that travels out throughout the system. Drum filter and sand filter are usually able to remove the bulk of the suspended solids, but sometimes the suspended solids can be so fine that you require what we call a polishing method. And to polish the water, we utilize the foam fractionation method to polish out any fine particles. I will now show you the theory of operations of what we call foam fractionation. The protein skimmer is the equipment that is used to achieve foam fractionation. Alright, what we have here is a milk that is placed in what we call a conical flask. As we know, milk is made of water and dissolved proteins. When we start to bubble the milk, what we see is a foam that is coming out from the conical flask. Essentially, what happens is the air bubbles being entrained in milk tends to pick up all of these small protein molecules and be up to the surface, and it is then carried out by the air particles. The protein skimmer works in a similar manner. By designing your protein skimmer to look like a conical flask and by providing it air bubbles, the air bubbles entrained in the liquid will pick up any fine solids and any protein molecules to be formed out of the water. Foam fractionation method is unlike the conventional mechanical filtration method, where a sieve is used to sieve out any solids. This relies on the surface tension of the bubbles to carry out any proteins. In the market, there exist several types of protein skimmers, but they all work on the same principles. A cross-current protein skimmer would mean that the water flow and the air bubbles are in different directions. For example, in this case, water flows in through the top section and flows down and exits the protein skimmer at the bottom. However, air bubbles is being created at the bottom, and due to the density difference, air bubbles actually travels up, and on its way up to the neck, it picks up any fine particles and forms up air bubbles containing these particles. So these particles can be removed occasionally on a daily basis. So this is what we call a cross-current configuration. On the other hand, we have what we call a co-current protein skimmer, in which the air bubbles and the water are flowing in the same direction. So how do they achieve that? So usually pumps will carry the water that you are wanting to process, and it passes through what we call a venturi. A venturi is a device that sucks in air upon fluid velocity. So it has a small constriction over here, in which when water passes through, it creates a vacuum and sucks in air. What you get is a water and air mixture. So the water will tend to move up along with the air bubbles, where the air bubbles will continue picking up any fine solids and foaming them out into a cup. The processed water will then flow down and exit through the protein skimmer this way. So this is what we call a co-current configuration. Generally, a cross-current configuration would be more efficient, as the water is traveling in a different direction from the air. But to achieve this cross-current configuration, you would sometimes need to utilize what we call a secondary air pump to generate airflow inside the protein skimmer. On the other hand, a co-current configuration, which is usually less efficient, but on the other hand, it is cheaper, as you only need a venturi to generate the air bubbles along with a pump. So it is a trade-off between capital cost and efficiency, and it's up to you to decide which is the more optimum for you. So this is how a protein skimmer looks like. As you can see, the rule of thumb, as the protein skimmer is taller, it maximizes the contact time between the bubbles and the liquid, and having a larger diameter would also generally mean it's rated for a higher capacity. I will then now move on to some of the theory behind the protein. It is also possible to run your RAS systems without a protein skimmer, and it is commonly done in a freshwater condition. However, in seawater, your pH is generally higher and your air bubbles are much smaller, hence making foam fractionation more efficient in seawater. Note that every time you feed, especially if you are utilizing formulated feed, you will change the surface tension and the protein skimmer might not work as well as if you were working trash fish. Having a protein skimmer generally also reduces system cleaning requirement by reducing the growth of bacteria. Essentially, by removing excess protein and fine molecules, the bacteria will not have so much excess feed to feed on, and reducing their growth. And since we know that biofiltration is an oxygen demand process, by reducing the amount of loading on the biofiltration, we can also increase the oxygen availability in a RAS system. It also ensures a cleaner water quality and improves UV transmission. And protein skimmers require little maintenance and is generally a low operating cost item. So if you were in a freshwater condition, installing a protein skimmer might not make a lot of economical sense. But if you're running in a brackish water or seawater condition, protein is very beneficial to your systems. Note that protein skimmers or foam fractionation cannot be for your drum filter or sand filter. It can only be used as a supplement to the existing mechanical filtration techniques, as it remains as a polishing method to remove out any fine solids and big protein molecules. So what are the rules of thumb to design a foam fractionation column? Again, we've earlier mentioned on that RAS system design is not designed for your starting density, but instead how much feed you are providing. So for every kilo of feed you are providing a day, you require an airflow of 20 liters per minute. You require a 90 cm square of a foam fractionation column area. So the typical foam fractionation configurations are in the 12-inch, 18-inch, and 24-inch dimensions. So generally, a 12-inch protein skimmer can process up to 5.5 kilos of feed a day, provided the protein skimmer is able to produce about 110 liters per minute of airflow. So two things to take note of. You are designing the dimension of the protein skimmer, and it is also important to make sure that you have adequate airflow inside the protein skimmers. How do you maximize the efficiency of the protein skimmer? Number one is to maximize the distance traveled between the rising bubbles. So this is mainly manifested as the height of the protein skimmer. Having increasing height of the protein skimmer would mean a greater contact time between your bubbles and your water that you wanted to treat. To maximize the efficiency of the protein skimmer, we should also create bubbles as small as possible. Given the same area, smaller bubbles would mean that the bubbles have more surface area corresponding to the volume of bubbles provided. And surface area is the key to picking up any additional fine particles and also protein. Maintaining a high pH would also help your protein skimmer. Usually, a dedicated pump must be used to supply the fractionation to ensure a correct water level. A foam fractionation is a very easy to build equipment. You can either buy them from suppliers or make them on your own like we did. If you are planning to make it on your own, make sure you follow the design criteria as provided earlier. You can make them out from simple PVC piping and also air pumps, or you can also use a cold current configuration where you subject the water pumps with ventures. We previously did not run the plant with the protein skimmer, and we often find difficulties running the ammonia to 0 ppm every day. But after we have run the protein skimmer, we are able to reduce the ammonia load on the system itself. So I would say, given the cost, the very small cost of building a protein skimmer, which can cost up to $300 to $200 if you're doing it on your own, or if you were to purchase it off the shelf from suppliers, which can cost up to $1,000 to $2,000, the benefits of having a protein skimmer greatly outweigh the costs. So that's all for now. The next lecture we will be going into biofiltration, which is the core of any RAS systems. Hi guys, thanks for enrolling to our course on the introduction of mud crab vertical farming. In the previous lecture, we have shown you how to design your own foam fractionation and what is the design criteria as well as the mode of operations. In this lecture, we will be talking about biofiltration. Biofiltration remains the heart of any RAS systems and is often the limiting factor in scaling up your aquaculture business. A good understanding of this biofiltration is crucial to ensuring that your crabs are being able to feed at a high rate as well as a low mortality. We will split this lecture into two sessions, with the first session being the theory of nitrification, and the second portion will be how to size your biofiltration plant accordingly. Biological filtration is a process that has been used for hundreds of years. The typical application for biofiltration is in a wastewater plant. On the picture over here, we see that this is a municipal plant in which bacteria is used to break down the waste into lesser harmful form before discharging into the environment. It is commonly found in the wastewater industry, the palm oil industry, and even your small size aquarium on a residential home. However, the difference between the hobbyist and actual aquaculture farm is the magnitude and cost effectiveness. Very often, aquariums at home are oversized, but because due to the cheaper costs in relative to big aquaculture projects, it is usually gone on unnoticed. However, biological filtration is an expensive plant to maintain, and it will form one of your most expensive capital cost items. But the goal of the biofiltration is to treat the dissolved matter derived from uneaten feed and feces, which manifests itself as ammonia. The concept of biological filtration is what we call nitrification. Note that there are a lot of terminologies for the same thing. And a nitrifying reactor or biological reactor is simply where this process takes place. An important concept about nitrification is to provide enough surface area for the bacteria to grow on. Also provide them with adequate food, good living conditions, and protect them against competition against other type of bacteria. What we have here from these three pictures are all what we call biological media. They simply can be made up of plastics. In this is what we call the traditional bio balls, and this is what we call K1 media, and this is what we call ceramic media. Essentially, they provide plenty of surface area for the bacteria to reside on and repopulate, as well as consuming ammonia into NO2 and NO3. Having that said, biofilters is essentially where nitrification takes place, and it's all about providing them with the necessary surface area for them to grow and thrive. They can come in many shapes and sizes. Note that you can also build your own bioreactor. You just require a tank and some media for the bacteria to go onto, and adequate aeration, and bacteria will definitely grow. However, selection of different reactor will depend on several objectives, and it will often depend on your feeding rate, size constraint, and oxygen availability. The goal of biofiltration is to convert ammonia into a lesser harmful form. So where is all this ammonia coming from? We have feed or fecal matter that is consumed by the crab or is produced by the crab, which will slowly dissolve in the liquid, which in our case will be the system salt water, and that will often form what we call ammonia. Ammonia is very toxic, and it needs to be kept as low as possible. The values that you should be targeting is 0 to 0.25 ppm. The goal of biological filtration is to convert ammonia into NO2 and NO2 to NO3. And how do we do that conversion? Ammonia is a food source for a type of bacteria known as nitrosomas. It is commonly known as a nitrifying bacteria. So what does this bacteria do? It consumes ammonia, and with the aid of oxygen metabolizes ammonia into the next form, NO2. And then NO2 is used to feed another bacteria called Nitrobacter, and when you provide Nitrobacter with oxygen, it is able to consume the NO2 and produce NO3. Is NO2 and NO3 harmful then? That's a valid question. NO2 and NO3 are known to be less harmful as compared to ammonia. So your goal of nitrifying is to convert ammonia to NO2 and NO2 to NO3 in the fastest times possible. How do you estimate the amount of ammonia that is going to be produced? Total ammonia production, which is the ammonia that is harmful to the crab, is a function of feeding rate, how much feeding rate we are feeding a day, and it's also a function of the protein content in the feed. Typically for trash fish, higher quality trash fish could mean up to 40% protein, while high protein fish meal can sometimes reach up to 60 to 75%. These are the two building blocks of where are your ammonia coming from. We have also other parameters, for example, how much ammonia is actually being released into the water, which is a function of your solid filtration, the type of crustaceans or the type of species you are farming, and this is a typical conversion rate to convert protein into ammonia. So let's look at the quick example. We have to estimate the total ammonia nitrogen produced by 10 kilo feed at 40% protein content. So assuming if you are feeding 10 kilos of feed every day, what happens? 10 kilos of feed multiplied by the protein content multiplied by the wastage, which is a function of your solid removal and your species of interest, and these two are just conversions. We can see that 10 kilos of feed will produce approximately 0.4 kilos of total ammonia nitrogen on a daily basis, which is approximated to be 3% of your total daily feed rate. And this is producing with feeding 10 kilos of feed at 40% protein. So what change to a higher protein source feed? There can be feeds that are high in protein such as BSF or even high protein feed. As you can see, feeding the same amount of 10 kilos of feed every day, but the only thing that changes is the protein content. My total ammonia nitrogen comes up to 0.48 kilos a day, which is approximately 5%. So what happens if I double up the feed amount, 20 kilos, while keeping the protein content constant? As you can see, my total ammonia generated while keeping the protein content constant. As you can see, my total ammonia generated is 0.96 kilo of feed a day. So what is the takeaway value of this? The ability of the biofiltration to control ammonia is only dependent on the type of feed and amount of feed that you'll be feeding in. Assuming that you are not able to control ammonia, the best way is to stop feeding, and the water quality will slowly get back to its original value. So why is total ammonia nitrogen important? Firstly, it determines how much biological surface area do you need. What do I mean by biological surface area? Biological surface area simply means the amount of media that you require to treat an amount of ammonia. So what is the design criteria? Firstly, you need to ask yourself, what is your objective? Are you trying to do fattening, soft shell crabs, or grow up? Having that objective stated, you then move on to decide how much you have to feed on a daily basis at the maximum capacity. For example, assuming that you have to feed your 1 kilo crab at 10% of its body weight, it means that on a daily basis, you have to feed your crab 0.1 kilo, which equates to 100 grams of fish. You use this feeding rate and estimate how much total ammonia nitrogen you will be generating, and then you estimate the amount of biofilters you need. It is very important to understand that nitrification in different salinity reacts differently. For example, you cannot just use the nitrification rates in the freshwater and apply to the seawater, because in seawater, nitrification is much slower. It is estimated to be 40% in reduction rates as compared to freshwater. This is the volumetric nitrification rate in freshwater and versus saltwater for the same bacteria. As you can see, most of the coefficients are the same, but there is a constant in front of the saltwater, which is 0.5 as compared to a 1.1 in freshwater, suggesting that freshwater nitrification is almost twice as fast as saltwater. So it is very important for you to estimate biological filtration in a saltwater basis. That's all for now. In the next lecture, we will talk about the different techniques used for nitrification and the different reactors that are available in the market and their corresponding nitrification rate. We will be designing your system based on the amount of feeding rate that you will be providing to your crabs. Hi guys, thanks for enrolling in the course for the Introduction of Mud Crab Vertical Farming. In the previous episode, we have talked about the theory behind biofiltration and the different nitrification rate between saltwater and freshwater, and how to calculate total ammonia nitrogen. In this lecture, we will show you the different nitrification rates of the trickling filter, fluidized bed, and the moving bed bioreactor. This will help you size your biofiltration plant in the future. There are often very different types of biological filters. They can be in a form of trickling bed, which is commonly found in wastewater industries due to their huge size. And we have what we call fluidized bed, that is commonly used in a cold water freshwater application. And lastly, we have the moving bed reactor, which is commonly used in the saltwater application. Firstly, let us talk about trickling filter. So trickling filter are known to be very reliable, and they're known to be very big. So a good place to spot a trickling filter is probably at your municipal wastewater plant, in which they are probably processing from a factory that has a runoff of wastewater. They're usually situated behind the factory with a 2 to 3 story high structure in which it only contains rocks inside and waters are trickled over the rocks. Trickling filter is easy to control the oxygen, and is also easily control the CO2 due to its water wet surface. So how does a trickling filter work? Essentially, you just have water that is pumped up to the top of the tank, and water is allowed to trickle over the rocks, and it goes out at the end of the reactor. As you can see, a simple way to build a trickling filter is simply just use an aquarium filled with rocks, and where you pass the water throughout these rocks, and the water will go through all the seams of the rocks, and this is where the beneficial bacteria will go on to uptake your ammonia along with oxygen to convert into NO2, and the other bacteria will convert NO2 to NO3. So what are the typical nitrification rates for this trickling filter? A good way is to estimate your total ammonia nitrogen given the formula earlier. I know that some formulas might be quite daunting to some of us. Therefore, we have benchmarked the performance for each cubic meter of media. As you can see, for every cubic meter of trickling filter that you use, which can be made out of simply rocks or pebbles, the nitrification rate can process up to 3 kilos of feed per day. So, the media cost is not that expensive as well because they are just rocks. Assuming that you have to feed a crab 3 kilos every day, you will then have to provide 1 cubic meter of this sand filter media. Or in other words, if you have to feed 9 kilos of feed every day, you will require 3 cubic meters of media. So this is how you calculate how much media do you need. Unfortunately, trickling filters, although they are very cheap, then they tend to be not very reliable. The reason is being so. As water flows through the seams through the rocks, what often happens is you might have algae or some sort of bacteria that forms a biofilm, and it tends to clog up the surface area available to treat the liquid. So you will find out after running your plant to 6 to 1 year, most of the seams have actually clogged up, resulting that you either have to clean out the rocks or just replace the media. So usually what do people do in this case? People tend to oversize 3 to 5 times bigger in terms of capacity and allow for the clogging to occur. So in this case, which is a wastewater trickling plant, what happened is you might have need 20% of your capacity, but you oversize them 3 to 5 times so to account for this clogging factor. Secondly, they are very efficient and they're very compact, and they're also very cost competitive in terms of removing ammonia, NO2 to NO3. However, they are really only suitable for cold water applications. Why cold water? Because essentially, we have talked about ammonia being processed to NO2 and NO3. This process requires oxygen. And in cold water, the availability of oxygen is higher. I've also included this link to help you design and operate any fluidized bed reactor. So how does a fluidized bed reactor look like? For those who are familiar with aquariums, this is how a fluidized bed looks like. It basically is just a small reactor in which it has a lot of fine sand that is packed into this reactor. And using a small current, the sand is continuously moved up and down the column. So why do they move the sand up and down the column? It is because oxygen availability tends to decrease with increasing water depth. So as the deeper you go into the meat, what you get is a lower oxygen. And we have discussed earlier that for the bacteria to consume ammonia to NO2 to NO3, you would require oxygen. So without the movement, which we call fluidizing the media, the bacteria that are situated at the bottom would not be able to perform nitrification that converts ammonia to NO2 to NO3. The bacteria at the bottom will move up to the surface, providing it with the additional oxygen. So this is also another clip of how a fluidized bed reactor actually looks like. One of the reasons why a fluidized bed has gained popularity in the recent years is because of a simple concept. The bacteria grows on the sand in an outward layer, so they form what we call a biofilm layer, which consists of a community of bacteria. Usually, the younger bacteria will reside at the core of the biofilm, leaving the older bacteria on the surface. However, the older bacteria are not as productive as the younger bacteria. Therefore, by fluidizing it, essentially you are removing some of the older bacteria by scrubbing them against each other and only keeping the productive bacteria. So now let's take a look at the nitrification rate of this fluidized bed reactor. Again, you can do it based on total ammonia nitrogen, or we can use our rule of thumb. For every cubic meter of media, you can process up to 30 kilos of feed a day. As you can see, by standardizing the bed and also incorporating a smaller media, you can increase the nitrification rate by 10 times, and the media cost is relatively cheap. Therefore, fluidized bed reactor is much more efficient as compared to the trickling filter. However, it is only readily used in the cold water and freshwater industry. The third is what we call the moving bed reactor. The moving bed reactor has been the backbone of warm water, salt water rust biofiltration. This media is not made up of sand or stones. They are made from plastics. As you can see, this is the moving bed reactor for a tilapia farm in the US, and this media, which we have over here, is a media that we have been using in our crab farm. You can see it is just simply a plastics with a lot of surface area built into, leaving the bacteria to stay inside or one of these fins. And this is a commercially available product called K1, cold rest media. So this is how a moving bed reactor actually looks like. So this is a similar plant from the tilapia farm. As you can see, it's just being air pumps and the result, and from the effluent from the drum filter. It is also commonly used in aquariums for hobbies. And this is how the medias are being agitated in a reactor. So similarly, you have bacteria that are growing onto this media that have the opportunity to not only stay at the bottom, but go up to areas with high oxygen content. So as you can see, that you only require a small air pump to rotate this moving bed reactor. So what are the nitrification rates of this moving bed reactor? Every cubic meter of media, you can process up to 6 to 12 kilos. Why 6 to 12? 6 is when you're applying it in salt water, and 12 applying it in fresh water. As you can see, the media cost is relatively expensive, and it is much more expensive than sand or pebbles. However, provide very reliable nitrification. So assuming that if I have to feed 2 kilos of feed every day, how much media do I need? The answer is you only need 0.3 to 0.4 meter cube of media. If I have to feed 18 kilos of feed on a daily basis, I will need 3 cubic meter of moving bed reactor. In our farm, we are using the moving bed reactor, and it has shown to be reliable in controlling the ammonia into NO2 to NO3. On a daily basis, we are feeding about 4 to 5 kilos of feed every day, and we have about 1 cubic meter of this media in our system. We are able to the ammonia to 0 to 0.25 ppm on a daily basis while feeding at this high rate. Biological filtration is often the limiting factor in any RAS systems. Increase your feeding rate while maintaining the same water quality. It is important that you have sufficient media to ensure that your nitrification is happening properly. That's all for this lecture. In the next lecture, we will talk about disinfection technologies, mainly UV, ozonation, and biosecurity to ensure that diseases stay away from your aquaculture system. Hello everybody. Thank you for joining the course on the introduction of mud crab vertical farming. In the previous lectures, we've talked about biofiltration and the different technologies that are used in processing the waste in the nitrifying system. We talked about trickling filters, fluidized bed, and as well as moving bed reactor. In this lecture, we will move on to focus in preventing pathogens in your recirculating aquaculture system. Proper disease control procedures is very important in a recirculating aquaculture system. It is because you are farming at an extremely high density, and any outbreak of diseases coming from bacteria, viruses, or parasites would have a catastrophic impact on your yield. The idea of disease prevention and control in a RAS system is to adhere to the prevention is better than cure. Firstly, you need to avoid the introduction of pathogens by buying from reputable producers and also choosing crabs that are fit to be farmed in the aquaculture systems. Decontamination of rust system is extremely difficult. We will explain in a little bit. Diseases can have varying economical impact on the business. Firstly, we always see a reduction in growth rates if the crabs are manifested with parasites, bacteria. Reduction in feed to conversion ratios, resulting in excessive feed costs. Thirdly is the mortality. Sometimes disease can also impact the product quality, and this disease is commonly known as the bitter crab disease, as well as lost opportunities. The first point of disease control is biosecurity. Usually, do not let visitors to visit your farm, especially if they are farming crabs on their own. This is to reduce the possibility of passing potential pathogens from their farm onto your farm. Do not let any visitors touch the water in your tanks that might potentially transmit any form of bacteria or viruses into your system. Make sure all your ground staff wash their hands and disinfect regularly. Pest control such as cockroaches, rodents needs to keep in check. You will also need a quarantine area for incoming fishes and any incoming crabs. Crabs have to be disinfected with potassium permanganate at 2 ppm for 30 minutes. This is how you disinfect the crabs. You place them in any cylindrical or rectangular tank. Add the correct amount of water followed by potassium 2 ppm and disinfect them for 30 minutes. Remember to provide them an airline to provide the crabs with oxygen. These are some of the crabs that are manifested with parasites. This is what we call rhizophilum barnacles. Over here, we can see that the gills of the crabs is infested with nematodes. Make sure all of your nets and tools that are frequently used, especially if they contact with crabs, and make sure they are disinfected regularly. What do you do in the event of diseases? Firstly, what you could do is to reduce feeding and improve the water quality. Usually, if your host and your environment is in an excellent condition, even with pathogens, there will not be a disease outbreak. Using medicated feed will sometimes have adverse impact on the biofilters. For example, usage of antibiotics are not recommended in rust. Antibiotics will not only kill off the pathogen, but it will also kill off the nitrifying bacteria that is used in the biofilters. Another way is to reduce the treatment temperature. By reducing the temperature, you reduce the growth rate of the bacteria, allowing the fish to fight the disease on its own. In the impact of diseases, try to perform a CFU count. A CFU stands for colony forming unit, and it gives you an indication of how much bacteria you have in the system, and try to isolate the bacteria to know what you're dealing with. Check on your UV functionality. The typical UV light lifespan is about 10,000 hours, which equates to about 10 months. In any recirculating system, there will be UV process embedded in the system. The UV destroys any DNA of any pathogen, regardless of bacterial or viral in origin. The UV that are utilized in the reactors are called UVC, and it has a spectrum of 200 to 280 nanometers. However, it is confusing as the bacteria require certain UV dosage, manifested as flux. But if you were to talk to the suppliers on sizing UV, they typically give you a benchmark of 1 watt per 1 meter cube of water. However, this is just a rule of thumb, as the UV light voltage does not give an indicator on how much UV dose is actually reaching the pathogen. To illustrate my point, this is a chart between UV transmission, UV dose, and UV transmission. As you can see, when the transmission percentage drops, the UV dose actually increases. So what are UV transmittance? Transmittance is a mechanism which affects the transfer of light from the UV light onto the water. For example, if your suspended solid removal control is not done well, you will have a lot of fine particles that is floating around the water. Now imagine your UV light trying to disinfect the water, but since your water is filled with suspended solid, it is not likely the light from the UV source can reach the pathogen, resulting in a widespread of pathogens in the system and your UV light useless. That is one form of reducing transmittance via turbidity. Sometimes there are other methods. For example, excessive organics in the water would also decrease the UV transmittance. One common problem we see in UV reactors is due to calcification. As you are running your RAS systems in saltwater condition, it is common for calcification to take place. Once calcification takes place in the UV lights, the UV is no longer reaching the pathogen effectively and hence reducing the transmittance value. And in return, reducing the actual UV dose that is used to kill the bacteria, rendering your UV ineffective. To have an effective UV transmittance, not only your UV light needs to be sized correctly with a low residence time, but your previous processes such as solid removal and biofiltration needs to be done well. Note that the UV effectiveness is very dependent on the previous unit processes. How do you operate a UV light? Firstly, you need to routinely check the sleeves for any deposition, mainly calcification or any form of deposition that might render your UV transmittance lower. We also proactively change out the UV lamp every 8 months, about 1 to 2 months before it is end of life. Residence time, speed of fluid flowing through the reactor is also important. Increasing velocity or increasing flow rate throughout the reactor would mean that it has a slower contact time, meaning that the pathogen will not be effectively destroyed. In the market now, we have seen a rise in ozonation. So ozonation is a water treatment process that destroys microorganisms and degrades organic pollutants by a gas produced by subjecting oxygen molecules to high electrical voltage. Ozonation, on the other hand, is toxic. However, it can be degraded with UV. So we have seen a lot of suppliers in the market who have tried to sell systems where they have ozonation first, followed by a UV system. And this dual system of ozonation and UV seems to be the perfect combination. In our plant, we are only utilizing a UV light. And the UV light we are using is about 90 watts. We have to proactively replace the UV light every 8 months. In some water treatment processes, it is common to include additional filtration steps such as microfiltration or ultrafiltration prior to the UV plant, or in our case, we are utilizing what we call a protein skimmer to remove any fine solids before it is introduced into the UV system to ensure that our UV is at its peak performance. So that's all for this lecture. In the next lecture, we will show you how all of these different unit processes work together to perform what we call the recirculating aquaculture systems. Thank you for joining our course on the introduction of mud crab vertical farming. In the previous lecture, we've talked about disease control using UV reactors and even ozonation. We have covered the consideration to design your UV reactors and how to incorporate them with your unit processes. Up to this point, we have covered the different unit processes that you require in any recirculating aquaculture system, starting from solid removal, which accounts for settable solids and suspended solids, followed by biofiltration, and lastly, disease control via UV reactors. In this lecture, we will be showing you how to integrate each unit processes together to form what we call a recirculating aquaculture system. This diagram shows the process flow diagram of our system. Note that we have modified the system that came from China to suit our needs. We first start off with crab houses. So our capacity is for 1,000 crab house. Waste from the crab houses will then flow through what we call the first retention tank, in which any floating solids will be removed, and any solids that sink to the bottom will go into the pump, followed by a check valve and into the sand filter. The first part of the system consists of what we call solid control, where the crab house and the retention tank will serve to remove any settable solids, whereas the sand filter acts as a method to remove any suspended solids. As we mentioned earlier on, due to the huge pressure loss across the sand filter, you would require a pump to do so. After pumping through the sand filter, the water is used to aerate and turn the biofilters. And this is where all my moving bed reactor media sits. After biofiltration, another pump is used to pump it up to the UV filter and recycle it back to the crab house. And the water is being recycled this manner. Note that we are utilizing a 2-pump system instead of a single pump. And the sand filters are being backwashed daily with tap water in order not to waste any salt water. The biofiltration is being agitated with the pump, and it also at the end to perform what we call aeration as well as circulation. This is the boxes we are using. It is bought from China by this company called Zhongkehai, and I believe it's available on Alibaba.com. Please note that there are other suppliers who can supply boxes, or you could even DIY your own boxes on your own. The dimensions of our boxes are as follows, and we have also carried out the CAD drawing to simulate how it looks like when you fit up together. Sometimes it is difficult to get the dimensions from the suppliers, and hence we have provided you with all the dimensions. This is our technical specs for all of our equipments that I am using. The centrifugal pump is about 29 meter cube per hour, whereas the total amount of volume of water in our system is about 40 meters cube. So this will mean a recirculation rate of at least twice every hour. And the pump is resistant to salt water. The sand filter breakdown, as shown as earlier, shows the breakdown of the different sands that we are utilizing in our sand filters. This is the retention tank volume of water and the biofilter volume. Note that we have 0.8 meter cube of media. For every media, we know that it can process up to 6 kilos of feed. So 0.8 meter cube would mean feeding up to 4.8 kilos a day. And this is the surface area for every meter cube. The moving bed bioreactor is agitated and aerated using a submersible pump, and as well as the pump that is used to pump through the sand filter. The amount of water we have in the system will consist of what we have in individual boxes, which is about 7 to 7.5 liters per box. And 1,000 box will give us 7.5 meter cube, plus the retention pond, plus the volume in the moving bed bioreactor, as well as the sand filter, which approximately gives us about 14 meter cube. Water is being cycled through the system at about 0.5 hours, which is half an hour per cycle. We have previously run this up to a maximum of about 700 to 800 crabs with organic loading of 300 to 400 kilos. We will now look at the important process control that you need to take care when you're running the RAS systems for mud crab. Essentially, the crabs need to be farmed at a balanced state. pH, dissolved oxygen, alkalinity needs to be sufficient in order to ensure that the crabs are farmed in a healthy condition. Another important parameter is salinity, which is the amount of salt that is dissolved in a body of water. Temperature is also a relatively important concept, followed by ammonia, NO2, and NO3. This is the specific operating envelope that we are utilizing. pH needs to be controlled anywhere between 7.5 to 9. In our case, we are using about a pH of 8. If the pH is lower than 8, we usually add dolomite into the system. Dolomite is commonly used in agriculture, and it is what we call magnesium and calcium carbonate. If the pH is too high, we usually perform some sort of backwash and top up the water. But this is usually not the case, because pH is usually dropping instead of increasing. Salinity. The optimum salinity that you'll be looking at is about 16 to 17 ppt. We can run anywhere up to 10 to 25 ppt, and that's fine. However, if you're running your high salinity and you have a lot of leakage in your system, sometimes adding salt will be very costly. For those who are planning to do this near the coastside, you will have a free access to seawater, and what you could do is to dilute seawater with a little bit of fresh water to achieve your salinity. The minimum salinity you need will be around 10 ppt or even lower, like 8 ppt, but we wouldn't recommend to do so. Providing the crabs with about 16 ppt is what we feel the optimum. For fattening, soft shell, And for grow out, you might want to run at a higher PPT. Dissolve oxygen. In general, you will require at least 5 ppm to do so. However, if your oxygen is insufficient, usually it would not harm the crab, but instead it will affect your biofiltration. As mentioned earlier on, biofiltration relies on the availability of oxygen, and it usually requires at least 4 ppm to function well. In the case of oxygen, do increase the amount of aeration you have in your system, either by incorporating air pumps or utilizing more ventures to increase airflow that is into the system. Temperature. The optimum temperature we found is somewhere to be 27 to 29 degrees Celsius. If the temperature is too low, your crabs will not molt that frequently. Ammonia, NH3. As mentioned earlier on, the goal of biofiltration is to convert ammonia to NO2 to as fast as possible. Ideally, you want your ammonia to be as low as possible, lower than 0.25 ppm, ideally 0 ppm. If in the event that you have high ammonia, do perform some sort of backwash or partial water change to change out the water, top up with new water. And to ensure that your biofiltration is working properly, make sure that the biofiltration process has enough oxygen, at least 4 ppm. Nitrite, NO2. Ideally, nitrite has to be as low as possible as well, in the range of lower than 0.5 ppm. Please note that the lethal dosage for nitrite varies with salinity. In a freshwater condition, nitrite is more toxic than ammonia because nitrite will bind with what we call the hemolymph and suffocate the oxygen. So this is known as called blood toxicity. Whereas if you're in a saltwater condition, greater than 15 ppt, the lethal concentration for nitrite increases because chloride ions will compete for the space for nitrite, rendering the organisms more resistant to nitrite in a saltwater condition. In the event that you have high nitrites, do perform some sort of water change to reduce the concentration levels. Nitrate is the last part of the nitrification sector. Usually, nitrate, NO3, is not that toxic as compared to NO2 and NH3. Concentration can go up to 500 ppm without harming the crabs, but ideally it should be as low as possible. Alkalinity. Alkalinity is what we call buffering capability, and ideally it should be more than 120 ppm. In the event that your alkalinity is low, do add in what we call dolomite or even sodium bicarbonate to increase the alkalinity. Alkalinity is what we know as the buffering capability of the liquid. With high alkalinity, your system is able to buffer against fluctuation in acidity. The key to controlling pH is to make sure that alkalinity is high. Lastly, calcium. RAS system designs for crustacean is very different from farming fish or other species because crabs will uptake calcium from the water. One good way to maintain enough calcium in the system is to add dolomite or calcium chloride will do the trick as well. Ideally, you want to be maintaining calcium about 200 ppm. We have run calcium levels from 120 to 400 ppm and it's fine. Ideally, you want the calcium to be as high as possible, which is in the range of 4 to 500 ppm. Inadequate calcium levels will often result in shell thinning effect of the crabs, and it will also impact the osmoregulation of the crabs. Sometimes, some farmers will actually complain that after fattening their crabs for 1 to 2 weeks, they will realize that the weight of the crab decreases. This is likely due to the lack of calcium in your system. The crabs are utilizing their shells in their body and uptaking calcium from their shells to perform some sort of osmoregulation. Lastly, we provide standard operating procedures on when to take specific readings of the mentioned criteria. So for readings like DO, pH, and temperature, salinity, you could use what we call a digital probe or even test kits to measure this. If you are using a test kit, so it will make sense for you to take multiple readings a day. For ammonia, NO2, NO3, usually we are using chemical test kits, mainly from Sarah. So for these readings, you can take them on a daily basis or every alternate days. Alkalinity, we are utilizing a titration kit. We can take it every other day, as well as calcium. Magnesium and iodine are not key values and you can take them every week. For the sand filter, we're recommending backwashing every day for 1 to 2 minutes. So that's all for this lecture. In the next lecture, we will start to embark our journey on understanding the biology of mud crabs and how to tune your RAS system specifically to suit the needs and the fundamental requirement of the animal. Thank you.
Hi guys, thanks again for enrolling on our course on mud crab vertical farming. So now we're just going to give you a virtual tour of our farm. So we're going to first start off with looking at the box. So right here we have the box that we have been using in our farm. So this is obtained from China. So to maintain a water level, you require what we call an outlet tube that is force-fed onto the box. So by having this, we can maintain an outlet tube as water will flow and fill up the box. So the lid is being sort of placed onto the box using this hole. So you just put in the cover. So and this is how the covers are being fit onto the boxes. So we'll now move into seeing how each of these boxes are held together. So we have one of my interns over here that's about 5'10". As you can see that he's still comfortably able to work on the third row. But if we were to ask him to try to work with the first row, you can see that it is relatively too high for him. What about working on the bottom row? So you can see that he has to sort of kneel down and squat down to work with the rows at the bottom. So it's important to consider the height that you're working with, especially in a vertical farm. And there will have to consider the ergonomics of when you're going to work. So I'm just going to show you where is the water actually coming from. So this is the overhead piping in which treated water is being recirculated back into the boxes. So the two pipes on the right that you see here is where the water is going into the box. It is being divided over here. So on the fifth column, it has a sort of valve inside that stops the flow from going into the box. So essentially, the pipe on the right control the top 5 row, and the pipe on the left controls the bottom 5 row. So now the pipe that you see in the middle here, which is like a bigger 1-inch, is the outlet of the water. So the water, after it flows out from the box, it gets collected in this bigger piping and flows through the drain. So each block will have its own dedicated outlet point. They are all connected to the drain and they'll flow to the first retention tank. So I'm just going to show you how it looks like when you have crabs inside the box. So notice here there's no water level. So essentially what happens is the crab has actually pushed out the tube that is maintaining the water level. So this is an important point to take note. So this is how, if we have a crab that does not do this, we prefer the outlet tube to be sort of screwed onto the boxes, because the crabs are often very active and they tend to sort of push out this outlet, and which will render your boxes out there's no water level. So in this case, what you see here, there is no water that's even going to the box despite the valve being on. So this sometimes happens if your inlet tubes are too plugged, and that will result in not having waters not being able to go into the box. So you see that we have barricades here. So this is to prevent crabs that escape from the box and to prevent them to escaping this enclosure. So this commonly always happen, even if you're farming them in vertical farms as well. So it's important to take note that the crabs, even though they can escape the box, do not escape this enclosure, because what happens is they'll hide below your desk, and when they die, they give out a certain smell. So here we have a cardboard that we often use. If you're farming crabs that are below 50 grams, you have to put this in, because what happens is crabs can escape from this hole and go to their other box, and even escape from this whole vertical farm setup. So that is about the box. Usually this is how we run it. And now I'll take a look at the water treatment system. So this is just a back view on how the water is being distributed into each individual rows. So now we're going to take a detailed look at the water treatment system by first looking where does the outlet water go first. So assuming the water exits the pipe via the outlet tubes and it goes to what we call the retention tank, and whatever is being flowed to the retention tank will be then flow through what we call the first stage, which is solid removal via this piping. So we'll just follow this pipe all the way into the first pipe, leads from the first retention tank all to the first pump. So this is the inlet of the pump. After entering the inlet of the pump. This is the outlet of the pump. So the pump goes to what we call the six-way valve that controls the sand filter. So right now it's on what we call filtration mode. You can turn it to backwash the sand filter occasionally on a daily basis. So after filtration, water sort of goes out from the sand filter via this pipe, this white color pipe, and it goes all the here, and this is the treated water after filtration from the sand filter, and it just travels down this pipe and it goes to the next process, which is biofiltration. So it goes down over here. Alright, it goes down and there's a series of ventures that aerates and circulates the biofilters. So this is the media that we were showing everybody earlier on. Just letting the camera focus onto the biofiltration media. As you can see, they are made out of this black color plastics, and they have a lot of surface area to enable bacterial growth on the system. So this is how we look at the biofiltration. You can see that all of the media are being circulated and aerated at the same time using the outlet water from the biofilters. So in which at the end of the biofiltration, the water sort of flows through a series of bricks and lastly into the last stage before it is being disinfected. So we have a small UV light that we have in the bottom, and it goes to the inlet of another pump, and it goes to the UV filter. So this is the UV tank, UV reactor, and it goes back up to the individual crab houses. So this is how the water is circulated in general. You can look at our process schematics and can just double check that everything is accordance to our surface layout. So remember that we talked about UV having to have a polished water. So this is what we call a protein schema that we made ourselves. It's used to polish the water just before going to the UV to ensure UV transmittance is high, and you can see that the scum that is produced from the protein schema itself. So what we have here is two dosing tanks. So these dosing tanks are tanks that in which we add chemicals into these tanks, and the chemicals are slowly being dripped into the system. So we want to dose chemical in a gradual basis, and this is how we do it, by putting them in these tanks and slowly let them drip out towards the knife. So that's all for how our plant generally looks like. You can also check out our YouTube and our Facebook page to see for any updates on the plant. So thank you.
Hi guys, thanks again for joining our course on mudcrab vertical farming. In the previous lecture, we have seen the basic biology of crabs, anatomy, and the habitats of which mudcrabs reside and populate. In this lecture, we will be talking about the growth rates, the typical growth cycles, and important growth data that you need to sort of support your financial models. So let us take a closer look. How do mudcrab actually grow? They go through a process called molting, or what we call adhesis. It is an extremely complex process, and it involves shedding off their old skeleton and gills and mouth into a soft-shell crab, and later on mineralizing their new shell. So this is a short video on the molting of another species called blue crab. So as we can see, the carapace have actually detached from the abdomen, and the crabs are now just intaking water to a process what we call water uptake to balloon itself up and push up the carapace. So you can see from this diagram how high the crab has actually ballooned in terms of height. Alright, and this is an important point in designing your vertical crab farm. You need to make sure that the height of the water in your boxes is sufficient for at least the molting process. As you can see, the crab is now about twice its initial body height during this adhesis process. So how the molting process works, it will continue absorbing water and continue ballooning itself up. And as you can see here, what happens here is it's actually slowly picking up, and its abdomen is actually detaching from its old shell. So how does the molting process begin with is usually by this process first, followed by slowly detaching their swimming legs first, followed by the walking leg, and lastly their claws. Sometimes it is also possible for the crabs to get stuck during this process. For example, they might get stuck in one of when they're trying to remove their swimming legs from the old shell. So what they typically do is they will just leave their legs in the shell. So this is why sometimes molting can be a stressful point, and you might sometimes lose some of the limbs in which it will regenerate later on. So just skipping forward, this is, you can see that the swimming legs are almost up, right? So this is what you see here, and this is almost what we see, the last part of the swimming legs. Each individual walking legs is also coming out as well. It's just slowly trying to get itself out from the old shell. So you can see swimming legs are out, the walking legs are almost done. The mouth are also up, lastly leaving the claws in there. Alright, so he's almost there. Okay, so this guy is fully out from his old shell. Alright, so at this point, if you decide to harvest them, right, so you harvest this guy over here, the shell will be soft, and this is what you call a soft crab. Note that a soft shell crab is not any particular species, but instead any crabs that are in the soft shell stage. So if you just decide to harvest them right now, put them in a freezer and sell them for later consumption, this is what we call soft shell crabs. But if you were to leave it under its natural conditions, for example in seawater, what you will find is that their shells will reharden because they're absorbing the calciums from the seawater, forming a hard shell. So this is how the molting process goes, and this is how crabs can actually shed off their old shells and grow into a bigger crab. Slide will then look into specifically how to identify the molting process. So essentially, the easiest way to spot a potential molting process is by observing the opening of the what we call sutures, which is connecting between the carapace and the abdomen. So if you see this starting to open, that means they're about to molt, give or take 1 or 2 days time. So another important point to also consider when you're trying to look for crabs that are about to molt is that they will stop feeding. Alright, the second stage is where it starts to balloon itself and continue lifting up its carapace, and it slowly comes up. Alright. What you will see here is trying to get out of the shell by slowly removing its swimming legs followed by walking legs. This is trying to remove its walking legs, and now it's fully out of the shell. So we break down the molting process to essentially 5 stages, meaning stage A, stage B, stage C, stage D, and stage E. Typically, we are more familiar with the stage C. So stage C is when the crabs are in their hard shell conditions. So this is the typical crabs you get from the restaurants, they are in the hard shell, they are alive, they're active, right? So at this stage, the crabs will actually go out, forage for food, sort of build up their muscles and consume shellfish and accumulate reserve. The crabs that you see are mainly in what we call stage C. When they're about to get to the what we call pre-edesis, pre-molt process, right, mainly characterized as D, this is when that they will start to reabsorb some of the minerals from their shells and slowly open up the sutures which is connecting the carapace and the abdomen. So stage E is when the sutures are so open and it starts to uptake water, right, just to balloon their body up and sort of perform that molting process of escaping from its old shell. Assuming that if it's newly molted and it manages to fully escape from its shell, all of the limbs intact, it will now continue to reabsorb more water and balloon itself up and absorb some of the minerals from the water to form what we call paper shell. Right? So the paper shell usually forms after a few hours, maybe 5 to 6 hours, and it will slowly fully harden back into a full shell to 2 days. Right? So typically what happens is also, after they get to what we call paper shell, or maybe one day after the molting or 2 days after molting, it will consume its old shell that was initially discarded and reabsorb some of that materials, mainly calcium, into their existing motif and sort of accumulate that resources that was lost in the old shell. So what are the weight gain after every molting process? So we have a table here that is mainly derived from our data. So just to note that the date 1 and date 2 are not the date when it molts, and it just means a sampling date. So generally what you can see is for crabs that are under 100 gram, after molting they will get to somewhere between 170 up the way, to 270, or 215. And the crabs from 100 to 200 gram size, after molting they'll get to about 250, about to 300 gram size. So if it's a 200 gram to a 300 grammer, well, after molting you'll get to about 400, 450, and a 300 gram size will gain up to about 500. I would say a general conservation amount is to account for about 60% increase in weight after every molt. So that's how we model how much post-weight gain we have when we are molting. So does it mean that your margin increases 60% after it molts? Not necessarily, it can be more than that. Why? So what we have here is H3. What's H3? H3s are crabs that are known as crabs that are having weights from 300 to 400. So that we call that H3. H5 are crabs that are ranging from 500 to 600. That is a naming system we use in Malaysia that follows the naming system in Indonesia. If you are in, for example, Philippines, you probably work with the naming system called M1, M2, OS1, OS2. Alright? So different countries have different naming system. So what happens if you molt from a 300 grammer to a 500 grammer? Not only you increase in weight, but you also jump between the weight classes. Right? For a H3 size, a 300 gram size, they typically retail for about 50 ringgit per kilo. That's about 12.5 US dollar per kilo. Note that these prices are only just an illustration. They are not reflective of the current prices. Right? So what happens after it molts? So after it molts, we know that it sort of mineralizes its shell, and then it goes to what we call stage C. Stage C is when their shells are fully hardened and they're just about to go about, and capture more food and sort of build up the muscles in their body. Right? It is almost impossible to see from the naked eye whether they're just molted or they're about to finish the end of stage C, meaning they're about to molt soon. Alright. So how do we test whether the crabs are actually full or empty? Note that in the we call water crabs. So water crabs are crabs that just molted and the shell is already hard, but they do not have meat, and you can't really sell them because they have no value to the restaurants, right? On the other hand, what we call meat crabs are crabs that have actually molted, forage for food, and build up efficient and strong muscles in their bodies, and this is what we call meat or full crabs, and they are ready to be sold to the customers. Right? So how do we grade between water crabs that just molted, have a hard shell, and how they have what we call full crabs? So we use what we call the grading method. It's mainly by pressing onto their shells, and mainly their carapaces and their abdomen by detecting for shell flags. The greater the shell dense inside, meaning that the crabs are actually watery in nature. If you press onto the abdomen and they are full, it often means that the meat is full inside the crab and is ready to be sold. So this is a short video on how do you grade crabs.
In the Australian mud crab grading scheme, we use letters A, B and C to describe the hardness of the shell. The hardness of a mud crab shell gives you a good indication whether they're full of meat inside or not. For females, you do not test the bottom of the shell because it's mainly made up of the flap. We test the top of the shell only. For females, you do not test the bottom of the shell because it's mainly made up of the flap. We test the top of the shell only by pressing firmly, checking for areas of softness or flex. In the C grade, it's soft, but it also has a clicking noise. That is a C grade, would indicate that is not full of meat. For the B grade, testing the top of the shell by pressing firmly. As you can see, it's solid in the center, but as you work your way up, you can see that there are areas of softness or flex on the shell. For the A grade, testing all over. In the center, very firm. As you move your way out, still solid. This is an A grade and is likely to have a full body of meat. For the males, we test both bottom and the top. Pressing firmly, very solid there, but as you move outwards towards the edge of the shell, you can see that there are areas of softness on the mud crab shell. Also at the bottom, there are multiple parts of the shell where it's soft. That is a C grade, indicating that it would not be full of meat. The B grade, testing the top of the shell, very firm. The bottom of the shell, most parts are solid, but you will find, for example, areas like this spot here where there is flex in those segments. That is an indication that it too is not completely full of meat. Therefore it is a B grade. The A grade, firm all around the top of the shell, in the center and towards the edge, and at the bottom, firm all around on all these segments. As with the females, we do not need to test the abdominal flap as there is no meat underneath either of them.
So the next popular question I often get from a lot of my students are, how long does it actually takes to grow a mud crab? Before we look in the pond setting or even the vertical farm setting, let's talk about what happens in the wild. Right? So this is from East Africa, mainly Kenya. As you can see, this is a plot between wet weight, meaning the weight of the crab, versus the age. How long does it take for a crab to reach 500 grams? So if I look at this chart and just draw a line down, it takes it about a year. Alright, that is pretty slow, right? Luckily, in this paper, he actually mentioned that the Southeast Asian breed, mainly the breed from Vietnam, from Philippines, from culturing Celia serrata, is about 70 to 80% faster than in East Africa per se. So typically what we see in the market is being able to grow 0 to 500 grams in about 5 months or so. So I've also spoke to a lot of specialists in the market that have also given us some sort of benchmark on how the growth rate is likely to be like in a pond, for example. So this is from Dr. Colin Shelley, which is the famous author from the FAO. So he actually gave us a benchmark from 300 to 700 grams in 2 to 3 months. So that's a 400 gram incremental in about 90 days, giving us a growth rate of about 4.4 grams a day. So what about if we look into more papers and more data out there in the market, right? So this is extracted from a paper, and we will take a look at its individual growth rate. So we can see over here, somebody in the Philippines will do it in the pond. They stock the pond with 14 grams up the way, harvesting at 215 grams. They did it about 131 days. So as you can see, the average growth rate is 1.5 grams per day. So let's look at something else. This guy is culturing in Philippines, mainly Celia serrata and Celia truncoberica in a pond setting, stocking at about 9.2 grams per day, mainly crablets, and they harvest at about 391 grams in 100 days. On average, they were growing it at about 3.12 grams per day. So let's look at somebody from Malaysia which claims to be able to do 250 grams to 400 grams a day in 30 days, which is an average of 4.92 grams per day. Alright, so there's somebody who's even faster. They could do it in cages, 315 grams to 425 grams per day in only 21 days. That's like 5.15 grams per day. So What is the take from this? I would say the average is somewhere between 2.5 to sort of 4 grams per day. Right, that's what we call the industrial average, right? So in the industrial average, meaning, you know, on the upper limit, you're looking at about 5 grams per day. Whereas on the lower limit, you're looking at about 1.09 to about 1.5 grams per day. All right, so this is to try to understand where most likely are you going to, you know, experience what sort of growth curve. If you're conservative, you can model your business model to about 2.5 grams a day. You're a bit optimistic, you can do about 4 grams per day. Okay, so this will serve as a tool for you to other people are claiming whether it makes sense. So for example, some supplies that can claim they can grow up to 0 to about 900 grams in about 7 months. So use that, calculate the average per day, and sort of compare it with the industrial standards. What you're doing in a vertical is not much different from what it's in. By growing them in boxes, you are only actually changing the possibility of cannibalism. So in other words, theoretically, by growing them in boxes, you should not be much faster than the pond per se, but your mortality would be lesser than if you were to grow it in a pond setting. You know, what is our sort of our growth rate that we were experiencing when we were trying to grow out in our system? So as you can see that for a weight class about 300 gram sizes, we were growing at about 2 to 3 grams a day, and on the upper side, we were doing about 3 to 4 grams per day. But if you were to look at the one sizes, we are seeing growth rates of about, you know, 1 to 1.5 grams per day, which is slightly slower. Based on our findings, we actually think that growing the crabs in vertical farm do not really accelerate the growth per se, but it actually sort of stops cannibalism. What we think is happening here is this specific set of data is really applicable to the box that we are using. So for those who are interested to see what sort of dimension size you are using, you need to go back and to the previous lectures to sort of scoop out what is the dimension of the boxes we are using. We have an interesting point whereby if you try to grow a 900 gram crab in the system, you will notice that feeding rate would drop when you place them in the system. So when you move the box, you'll see that their feeding rate increase. So we sort of notice that this happens to mud crabs as well. By confining them in such a small space in box, what we see is, especially with bigger crabs, anything beyond 500 or 600, we see that there is a decrease in the feeding rate. Interestingly, this actually match up with the findings found in the lobster industry. So similarly to crab, lobsters are also a highly cannibalistic species, and everybody's been trying to grow them in boxes. So what they found out is that if you put the lobster in the boxes and it grows up to a certain size, after exceeding that certain size, you will see that the mortality is very high. And that mortality is due to the lower feeding rate of lobsters that are being enclosed in a box. Alright, so that's all for this lecture. In the next lecture, we will look at the different production methods of mud crab, whether it's a soft shell or from wild or from pond or hatchery and so on and so forth. So that will give you an idea on who is doing what and what sort of technology are being, whether it's a soft shell or from wild or from pond or hatchery and so on and so forth. So that will give you an idea on who is doing what and what sort of technology are being applied into farming different crabs for different market demand. Thanks again for joining our course on vertical mud crab farming. In the previous lecture, we have shown you the typical growth rates in the boxes as well as conventional farming methods. In this lecture, we will show you the different production methods that are used to currently farm crabs and what different technologies are being applied at each different stages. There are currently 5 main mud crab production methods, the first being wild catch, the second hatchery, third the grow out stages, fourth soft shell crab, and lastly crab fattening. We will go in depth on production methods that are currently dominating the market. Unfortunately, in most parts of the world, wild catch still represent a major supply for mud crabs. This is true for the countries like Malaysia, Indonesia, Bangladesh, Sri Lanka, India. Wildly caught crabs can be and are usually cheaper, but their quality and supply are inconsistent and is really dependent on seasonal availability. However, in the recent years, we have seen the supply of bigger crabs that are usually limited. This ranges from anywhere between 500 grams and above. Popular locations to find crabs can be Tarakan, Makassar, Bangladesh, Medan, and so on and so forth that were mentioned earlier. The second mode of production is what we call the hatcheries. In Malaysia, we know of two hatcheries, one in Perak and one in Sarawak. In Philippines, there are also many smaller decentralized groups, and this is the same for Vietnam. In general, there are not a lot of hatcheries, and it's difficult to consistently produce crablets. The price for crablets in the 80 to 160 gram range are about 20 to 25 ringgits per kilo, which is about $4 to $5 US. And they usually have to pre-order in order to get a consistent supply. Having the stock from hatcheries, they are usually being able to being stocked in ponds. The stocking size is about 1.2 to 2 cm carapace width, and it's about 2 to 3 grams. So this is how the baby crablets actually looks like. So these are used to stock in the different ponds at varying density, whether you are doing a monoculture or polyculture. It is also popular to do it with milkfish and shrimp, and of course tiger. However, do take note that the risk of doing a polyculture with other species like a shrimp, because diseases like Vibrio could potentially spread between the species. It is commonly also possible to grow them up to female that have eggs, or in other words, for them to grow them up to about 500 grams, where they are in high demand, especially in Singapore. Apart from growing them in ponds, you can also utilize what we call as a pens. So basically, pens are slightly different from ponds. Essentially, they're just a barricaded forest, and this is how it actually looks like. This is one of the projects in Fiji in which they will actually put up some structure and nets in the mangrove forest itself without removing any of the initial forests. So basically, you stock the ponds with these crablets when they are about 1 cm carapace width at about 1,000 to 10,000 per hectare. The idea of using mangrove pens is the crabs are also able to sort of forage their own food apart from the feed that you provide and seek shelter in this highly dense mangrove forest. So 3 types of methods that are currently dense mangrove forests. So 3 types of methods that are currently used to farm crabs. So this is what we call in a traditional pond setting. It's just a mud pond followed by a netting around the pond. And this is what we mentioned early on in the mangrove pens. Sometimes if your crablets are too small, you might want to nurse them to a slightly bigger size. Without doing so, your crabs will tend to escape from the pens as the nets cannot be too fine. So this is how you sort of build a small nursery for the crablets. The 4th kind of production method is crab production. As mentioned earlier on, softshell crabs are simply crabs that have molted and you then harvest them. So what do you do in this mode of production? Essentially, you stock your system with what we call smaller muds from the grams of 80 to 120 grams. And they are held until they are molted, and once they're molted, they are chilled and frozen. So crabs are typically held in these systems for a few weeks, mainly 3 to 4 weeks. And after they molt, they will just put it in the fridge. The problem is, with this kind of production system, you have to harvest them when they're molt. Hence, you're going to require a 24-hour shift for morning and nighttime monitoring. So a morning crew will be in charge of feeding and cleaning up the boxes and the night crew will be more in charge of monitoring for any crabs that have molted and placing them into the freezer. Initially, the cellular systems were developed for soft-shell crab farming. This is to reduce the cannibalism between the crabs when they are about to molt. So traditionally, you can do them in boxes like these, where each individual boxes you held one crab. And this is the same cellular soft-shell crab system, which is very similar to the ones that we are using. However, out there in the market, there can also be other forms of soft-shell crab system without using the vertically stacking up, commonly found in Indonesia, Myanmar, and even India. So these are how the individual boxes are spread over a pond. So a pond that could be used traditionally for mud crab grow out could be also used for soft-shell crab farming. The only differences is that you have to provide them individual boxes to prevent them from cannibalizing from each other. Each individual box up to one crab, and they are monitored throughout the day. And how do they move around these boxes is by pulling a sort of a mechanism that sort of push and pull the boxes. The last type of production method is what we call crab fattening. As we have explained earlier on, when crabs are just molted and their shells have hardened, typically you are not being able to see any sort of difference using the naked eye. But if you were to use the conventional grading method, as explained earlier on, by pressing onto their shells, what you will see that they are usually not full in meat. And hence, crab fattening is a process in which you get crabs that do not have what we call meat, and which are common water crab, and you fatten them up in a short period. So by buying crabs that are watery and feeding them for 3 to 4 weeks, you can bring up to a full amount. Typically, water crabs will retail about 30 to 40% original full meatiness crab, and there will be a typical trading reject about 5%. Usually, water crabs do not have any demand in the market because they cannot be sold to the end consumer. So what you are doing for fattening is to buy this discounted crabs from either rejects or during harvest and fatten them up in individual boxes like these for a very short period of time, and you sell them up at their full original pricing. Usually they will need time to feed and grow meat into their shell, and because it changes their protein content in the body. Crab fattening is economically attractive provided that you are able to source enough water crabs, either from harvest or from the farms. You are usually able to fatten up mud crabs in about 15 to 60 days, depending on the size. If you are fattening a 300-gram water crab all the way to a full size, you're going to take about 2 weeks. If you're fattening a 500-gram size crab, it takes all the way from water crab to full crab in about 28-30 days, and they're usually being able to feed about at least 3 to 5% of their body weight. In some systems, it is also possible to fatten females to achieve what they call a full egg mass in the body, as seen as here. So this is a video on how a water crab can be fattened up to this fullness. So that's all for this lecture. We hope you have understand the different modes of production that currently exist out there in the market, and how they are used to achieve a different mud crab production. In the next lecture, we will talk about the different mortalities in each individual systems. Hi guys, thanks again for enrolling in our course farming. In the previous lecture, we have shown you the different production methods that are commonly used to produce mud crabs, from wild catches, ponds, vertical farmings for soft-shell crabs, as well as vertical farmings for crab fattening. In this lecture, we will be discussing the typical mortalities for each of the systems and each of the specific technologies that are being used for mud crab production. Your profit. It is important to take note of mortality of the farming technology that you are using, as your profitability will greatly depend on this factor. As you will see in subsequent lecture, mortality is one of the very sensitive parameters that will actually change or make your It is important to take note of the mortality, as your profitability will depend on one key parameter, and it's very sensitive on mortality. Essentially, the mud crab trade is a live one, meaning a live crab is worth 80 ringgit per kilo, and when it's dead, it is usually worthless. Before we start off to look at the mortalities in vertical farms, let us first look at the typical mortalities if you were to experience a pond-based farming or even what we call traditional conventional methods. In ponds, the key factor to reduce mortality is what we call stocking density. As you increase the stocking density, what actually happens is the crabs will have a higher chance of encountering each other and therefore resulting in cannibalism. Typical stocking density can be up to 0.5 to 1.5 crabs for every meter square. And with this kind of stocking density, mortality can be as high as 67%. If you are stocking up to 0.2 crabs per meter square, you can sometimes have a mortality of 85%. Or in other words, survival rate can be 15%. However, survival rates from 20 to 86% has been reported in mangrove pens, but that depends on different stocking density. So what we have here is extracted from one of the papers. This is the name of the paper. As you can see that if the crabs are being grown in what we call the mangrove pens, which was discussed earlier by sort of netting off a specific section of the mangrove forest in which you will stock your crabs, survival rate is similarly 31%, which is mortality is about 69%. However, if you start to put them in cages, you can see that the survival rate increases up to 53%. So this is probably due to the fact that the crabs are being isolated from each other and hence reducing cannibalism. Further breaking down the typical mortality that happens in a pen culture. So what happens generally is you're going to have 20% of crabs that will escape from your system, and about 22% that will escape from your system, and about 22% is attributed to what we call cannibalism, either by cannibalizing each other during the hard shell stage, or whereas it can also happen in another way by crabs that are cannibalizing on crabs that are currently molting. So one good way to reduce cannibalism during the molting process is to provide them with adequate shelter so that the crabs can actually hide and perform adhesis. You can also see other factors will contribute about 10% to the overall mortality, and this is also another important point: molting weakness and molting difficulties. As we have discussed earlier, molting is a very complex process, and we can see that 22% of the overall mortality is attributed to this point. If we were to look at the vertical farming system as compared to the pen culture or the pond culture, what you are essentially removing by using vertical farming is only the cannibalism. It is often very hard to change the molting weakness or molting difficulties because that is the inherent mortality in the process. By managing your vertical farming, everybody closes the doors to each of the crab houses. What you can also ensure is to reduce the amount of escapees that are being farmed, because essentially crabs are very prone to escape from your system, and that is also evident if you are even using vertical farming as well. So what is our mortality when you're trying to farm crabs in a vertical farming system? So this is the mortality result that we had a while back. So it's what we call mortality root cause analysis. So similar to the previous findings, molting failures is accounting for about 20%. So this is what we call the inherent molting failure that the crab faces when they're growing out in the system. However, there are also other sort of subsets of reasons why the crabs are dying in the system. For example, 21% is due to what we call lost limbs. So when we first started out the system, we didn't have a very good knowledge on how to run your water quality. So when you have a deteriorating water quality, or your water quality is fluctuating too much, usually what happens is the crabs will tend to lose out their limbs and they eventually die. 29% of the time, we are not too sure why the crabs are dying. We sort of attribute this to probably diseases and inadequacy of the system being too small for the crabs. Another big portion of a mortality system is what we call TM, which we categorize as transport mortality. As you can see, it accounts for 25%, and it's one of the major reasons why mortality is very high in especially a system like us. We will explain a bit more about these individual root causes. And lastly, the smallest part is erosion. And this is probably shell disease that is slowly eroding onto the shell of the bacteria and eventually causing secondary infection and kills. So start off with molting. These are all pictures that we have accumulated when the crabs are being farmed in the system. So what happens to them is generally they will try to open up the sutures of their carapace, eventually die. So if we were to look at the traditional literature on what constitutes to this phenomenon, usually they will attribute failure to molt due to low temperature or nutritional causes. So in one experiment, it shows that if crabs are held between 27 to 30%, they're usually successfully molted. But if they are held at 20 to 22%, only 17% of the crabs molted in the same period. This is sort of the same as the lobster industry, as one way to induce molting is to increase the temperature in which the lobster are held. However, in our case, we are always farming in about 27 to 30 degrees Celsius. And why are we still seeing what we call failure to molt? It is essentially due to nutritional causes. So we have said earlier on that our boxes are probably too small for the crabs to be able to feed at a high rate. So this is specifically true for crabs that are above 500 grams. As you can see, by putting them into the system, you will see that the feeding rate decreases from about 3 to 2%. This is also evident when you're trying to farm big crabs, 1 kilo, and farming them in our system can generally result them in the feeding of about 1.5%. So one of the biggest assumptions that we have overlooked and most of our clients have overlooked is the space constraint of the box. We have also mentioned earlier on that crabs in the wild, they do move around and forage for food, but enclosing them in such a small area, and this is usually what happens as it manifests as a lower feeding rate. So this is a small chart on the typical molting efficiency and the success rate of the crabs in our system. And note that this data is specific to the crabs that are farmed in our boxes. For more dimensions on the boxes that we are currently using, please refer to the previous lecture to look at the dimensions that we have in our farm. So as you can see, that we first break down the analysis into different weight categories. H0 being crabs from 0 to about 100 grams. H1s are crabs from 100 grams to 200 grams. H2s are crabs from 200 grams to 300 grams. And H3 are crabs from 300 grams to 400 grams, and so forth. So how do we calculate the number of molted crabs? So what we use is two variables. Firstly is the molted percentage, meaning out of 10 crabs, how many of them actually molted in the period that we were looking at, and molting efficiency, which is defined as how many of them that try to molt and what is their success rate. So for example, as you can see, for H0 crab, within our window of observation, all of them, 100% of them try to molt, and they have been molting with a success rate of approximately 90%, which gives you an overall success rate of 90%. As we can see, if we move up to the first category, H1, about only 50% of them try to molt. So assuming that you have 10 crabs in the H1 category from 100 grams to 200 grams, only 5 of them try to molt. And out of the 5, only 70% of them is successful. So that gives you about an average of about 40% success rate. As we move up to higher categories, what we generally see is two things. Number one is at the same period, the amount of molting decreases and the efficiency also decreases. So if you will try to farm a crab that is farming from 300 all the way to 700 grams, you will realize that your success rate is only about 3 to 5%, trying to get them to molt from 300 to 500 grams. At this very low success rate, it is not likely that you can achieve a profitable business. And hence, what is our recommendations? So if you are either trying to use the same box, we would only suggest you to try to do a grow out maybe up to maybe H1 size, in which after the molt there will be somewhere between 250 to 300 gram size, very close to the marketable size. The marketable size is about 300, so essentially you're going to need maybe H2, which is a 200 to 300 gram size. After that molt there will be 350. So the other way to solve this problem is to try to use a bigger box. The next one of the biggest mortality that we have in our system is what we call transport mortality. Crabs are known to be what we call an aquatic species, but however, the industry do not transport them as such. The crabs are always transported in a dry environment, meaning they'll pack them in styrofoam boxes and so if you are running even an export market, usually your crabs will have to be sent from, for example, India to Singapore via air flight. And due to the transportational cost, people tend to pack them in dry boxes and without any water. This is to reduce the weight and in return reducing the logistical cost. However, if you were to take out a crab from its aquatic conditions onto a dryland conditions, they are able to survive, but not for a prolonged period, probably to 6 to 7 hours. Anything beyond that, usually you will result in what we call the stress that is induced to the animal. And this is one of the major reasons why crabs are so expensive, because it is the mortality that has to be accounted for throughout the supply chain. For example, every time you're packing a crab, you are handling them, you're grading them. As you can see from the previous video that how evasive is the grading process by pressing onto the shell and sometimes even cracking it. So exposure to breeze is another feature, being too high or too low or abrupt changes. So apart from air flights, what happens is once the crab gets into the specific country that you're going to, for example in Malaysia, the crabs will land in probably Kuala Lumpur or Senai and is then transported to several other states with bus. And note that they are usually just placed under the boot of the bus, which is really very hot. And also time is another factor to consider. From all the way to harvest and to the market, it can sometimes take about 3 to 4 days, which is really stressful to the crabs. And when they are transporting, usually they'll lose some of their weight due to starvation. And crabs in general will accumulate ammonia in their body, and they will need what we call water to purge out that ammonia that is accumulated in their bloodstreams. So the important factor that we want to sort of remind everybody that is your source is very important. And just whether they are dealing with crablets or whether they are dealing with crab fattening or even for trading purposes, they need to know that you are farming them and you're not holding them for only 2 to 3 days. And you can reduce the mortality just by ensuring that the supply chain is robust enough up to about 30% mortality. So I will show you our different supplier results. So we have here 3 suppliers, supplier A, B, C, that have been supplying us water crabs for fattening. As you can see, supplier C, if I just place a crab 2 days into the system, the mortality is about 60%. Whereas for supplier B, your mortality can only be 37%. But look at supplier A. The 10 days mortality is only about 10 to 15%. So what we are trying to show you is there are all the different crabs from different suppliers, but they're all placed in the same conditions. Why do they vary in terms of mortality in such a great manner? The only difference between supplier A versus B and C is that supplier A have what we call a robust supply chain. meaning at every route of the supply chain, supply A incorporates what we call a dipping system, in which crabs are removed from the styrofoam box and the dead crabs are being removed. Whatever that is alive is placed into water, being salt water or even brackish water, to let the crab sort of regenerate and recover from the stressful supply chain before sending it to us. So you need to understand what is your supplier doing with the supply chain. All right, they have to make sure that their supply chain is robust and they have sort of a good understanding of the crabs. So what are the crabs to avoid? Generally, you need to avoid crabs that look dehydrated, that have bubbling through their mouth, crabs that are weak, sort of the crabs that have barnacles, which indicates they haven't been molting in a long time, lost limb, broken shells. Broken shells will not kill the crab directly, but usually it will lead to secondary infection. Crabs with parasite, this is what's a rhizophyllum barnacle looks like. Discoloration of shell and shell diseases. Alright, so this is a typical crab that has shell disease. So the bacteria will actually eat onto the shells and perforate the shell, and then you have secondary infection either from fungus or some sort of other bacteria that infects the crab. Shell with discoloration are also crabs that have accumulated a significant amount by moving across acidic soil. When they have accumulated a huge what we call deposits, it will usually lead to growth retardation and death. So in terms of mortality, this will also constitute to mortality in your systems. Right, crabs with barnacles this is what that looks like. It basically means that the crabs have not been molting in a very long time, so it's been so long that the barnacles have actually grown onto it. Sometimes if your crabs have a lot of barnacle, it can generally reduce the perception of the product and of course leads to a lower market value. So crabs with lost limb also means that it is probably due to or it is exposed to too much dry environment. Usually what happens is it will tend to drop off their legs because they are stressed. And lastly is what we call crabs with parasites. So this is a disease that is not very well understood. Essentially it is and is often mistaken for a female crab. So what we have here is you can see that this is an abdominal flap, and it has one of what we call that looks like an egg sac. But for those who are more familiar with the crabs, and if you look at previous lecture, this is actually not how an egg sac actually looks like. This is what we call crabs infected with rhizophyllum barnacles, in which they convert a male crab into a female and changing their sex organ. So we highly recommend that you do not take in any crabs of any sort that have any sort of parasites, bacteria and diseases, because this is how it will attribute your system to be susceptible to diseases and eventually resulting in high mortality. Right? So that's all for this lecture. Crabs of any sort that have any sort of parasites, bacteria and diseases, because this is how it will attribute your system to be susceptible to diseases and eventually resulting in high mortality. Right? So that's all for this lecture. In this lecture, we've shown you the typical mortality if you were to farm in a vertical farming system. So the mortality for grow-out can be up to anywhere 30% to 40%. So you need to look at, and we know that the mortality is size dependent. So one way to avoid mortality in the system is to avoid molting. So how do you do that? So we specialize in what we call crab fattening, in which we buy water crabs, fatten them to up a period in their full, and we sell them before they can molt. So for those who plan to farm big crabs in the system, this vertical farming is really only applicable if you are trying to do fattening, as you are trying to avoid the molting process. But if you were to try to do grow out, you are only realistically looking at about the size about 200 to 300 grams, in which after that will be too costly to incur. Another potential business model is to look at soft-shell crabs, because soft-shell crab tends to molt at about the H0 size, which is about 800 to 120 grams. As you know, the mortality there is about 20 to 25%, which is still something that is worth to consider. So that's all for now. The next lecture we'll look at the supply chain of the business and how the crabs are being transported from one country into another, and how much time we actually spend during the supply chain. Hi guys, thanks again for enrolling in our course on the mud crab vertical farming. In the previous lectures, we have talked about the mortality of mud crabs, We have also covered the biological aspects of the crabs, as well as how to size your system accordingly to achieve your objectives using RAS system design. The next sequences of lectures will focus on the macro view of the industry, and we will first start off with the crab supply chain. So we have earlier talked about the typical habitats in which the crabs will reside. They usually stay in what we call mangrove forests, in which the water over there is what we call brackish water. They can also reside in what we call nipa forests as well. Usually crabs are caught in good numbers during the high tide, and this is probably due to the fact that the rising tide might bring more natural food into the inlands, and which crabs will forage around, and they are being caught during this period. The low tide starts again, they will again burrow into the mud. So if you were taking crabs from the wild, the first thing you will notice is that the supply is not constant, especially when you have the new moon or the full moon, in which the new moon is the first day of the lunar cycle and the full moon is about the 15th day on the lunar cycle. So during these two periods, what you generally see is a higher tide due to the gravitational pull of the moon, and this is where fishermen usually are able to find. So indicative that the supply sort of looks like a sinusoidal cycle, in which the peak sort of reaches during the full moon and the new moon, and when it's during the in-between, you get what we call a lack of a lower supply. However, it is important to note that the demand usually do not coincide to the lunar cycle, because consumers do not usually plan out their crab feasting activities according to the moon phase. It will generally coincide to festive seasons, or in other words, probably due in the weekends. So take note that your supply generally does not match up to the demand almost on a monthly basis. It is also important to note that usually the crabs during the new moon period are usually fuller. For example, you get less water crabs during the new moon, and you tend to get more water crabs during the full moon, because what happens during the full moon is crabs usually tends to molt around the period according to the lunar cycle, and once the fishermen catch them, probably one day after the full moon, and they're probably just molted, they're usually what we call water crabs. During the full moon period, there's a higher probability of getting water crabs as compared to the new moon period. So how does logistics actually looks like? So this varies from countries to countries. So first I will talk about Malaysia. Malaysia usually get their wild catches from Indonesia. What happens is they get it from a place where we call either Makassar or East Kalimantan or even Papua. So goods that are coming from East Kalimantan, the fishermen will usually sell to the first trader in East Kalimantan side by about 2 to 3 p.m. in which the first trader will aggregate all the volume from the fishermen and sort them out and start to pack for a shipment that goes to Tawau in Malaysia around 9 p.m. So it will then leave by boat from East Kalimantan all the way to Tawau and reach the next morning about 8 p.m. where a second trader, which is the importer from the Malaysian side, will then receive the goods or repack some of the crabs and redip some of the crabs in water and repack them to be exported to some of their other buyers in West Malaysia side. So it typically gets to West Malaysia slightly in the evening, about 8 to 9 p.m. in which the West Malaysia buyers are not able to send to the restaurant, because usually restaurant operates in the evening time and you have to send your crabs maybe at 4 to 5 p.m. So it is likely that they will miss the timing and they'll have to send the crabs the following day. So this is a 3-day supply chain. And please note that sometimes once the crabs are sold to the restaurant, it'll probably take another 1 or 2 days before they are sold to the end consumer. So that adds another 2 more days on top of a 3-day supply chain. So in total, you are looking at about 3 to 5 days of the supply chain in which the crabs are being harvested and reaching the end consumer. And this is also assuming the fact that the fishermen are able to catch their volume on that day itself. So usually what happens is fishermen might also catch 1 or 2 days earlier, keep the crabs on their side, and sell it to the first trader. So that adds another 2 more days on top of a 3-day supply chain cycle, making the total supply chain about 7 days. So this is important to take note the typical logistic and how long does it to the end consumer. So this is for Malaysia. What about the other type of supply chain? For example, if you're talking about Vietnam, so Vietnam mainly gets their supply from this province Cà Mau, which is the southern tip of Vietnam. The farmers which are farming the crabs would then sell it to the first-hand trader, and the trader will receive them about 7 to 8 p.m. at night, and they will start to pack and send the goods from Cà Mau all the way to Ho Chi Minh, which takes another 9 to 10 hours by car. So it reaches Ho Chi Minh the next morning about 6 a.m., in which the second trader will then repack and sort out some of these dead crabs and send the goods from Ho Chi Minh, will depart Ho Chi Minh by 10 or 11 a.m. to China. So it will probably reach Shanghai or Fujian about 3 to 4 p.m. clearing the customs, and then it is then diverted to the restaurants. So this is a 2-day supply chain. So a 2-day supply chain is also commonly found in Philippines. If you're located near to Manila, you should be able to do a 2-day supply chain as well. So what's the difference between a 2-day supply chain and a 3-day supply chain? Essentially, your price is really dependent on the efficiency of the supply chain. The more you have to go through different buyers, the more you lose out in terms of profitability. For example, one of the reasons why the wholesale price of Vietnam is very high is because they have actually priced with the China price. Essentially, your Chinese buyers are competing with your local Vietnamese buyers as well. And given the fact of economics, the seller will always choose the highest price. But this is often not the case in, for example, Indonesia. If you look at Indonesia's pricing at the moment, it is still slightly lower than the overall global pricing, which is usually determined by China. The only reason why it's not able to equalize the price fully to China is because due to the ineffective supply chain. For example, Indonesia often require moving the goods through Malaysia. For example, the East Kalimantan case, where the goods go to Awal, which is in Sabah, and then redistributed to West Malaysia or China or even Taiwan or Japan. So your supply usually often determines your pricing. It is important to pick a country, especially if you're farming the crabs, to be in a location that your supply chain is directly onto a big market, for example, China or Singapore. One of the supplier acceptance tests that we do on our side is to ensure the kind of quantity that your supply can actually produce. For example, if you were to buy in places like Malaysia, back in the past, Malaysia used to have a healthy volume of crabs, but due to overfishing, the location does not supply such amount of crabs anymore. So for example, if you were to call up your Malaysian fishermen or farmers and request them for 1 ton of crabs, what you're actually doing is you're only enticing them to start catching earlier. For example, if they know they are not able to give you that amount, they will try to catch probably 5 days earlier to make up for the volume to be sent to you. So what does that do in that case? Essentially, you are lengthening your supply chain by enticing your farmers to start catching earlier. So what happens is, by doing so, you usually see a higher mortality because the fishermen are indeed catching the crabs much earlier than you anticipate. One of the first QC tests that we do on our suppliers is to make sure their location can indeed supply the kind of volume that we are looking for. So that will reduce the amount of time the crabs are being harvested up to the point that it's being consumed. So this is a short breakdown of all the typical margins throughout the cycle. So this is a Malaysian case. So for example, the crabs usually are sold by the fishermen to the first exporter at about 15 to 16 ringgit per kilo. So the exporters buys them and experience sort of a mortality and requires a margin of, let's say, 25%, and it becomes 22 ringgit per kilo. And it then sells on to the next guy, which also experiences an 8% mortality and requires a margin of 25% and brings it up to 31 kilo. And lastly, is being sold to restaurants, in which it is experienced also about 10% mortality, and they require usually a higher margin of like at least 50%. And so this is how a crab can start from 15 to 16 ringgit per kilo and end up at the consumer side at 62 ringgit per kilo. Usually the margin is taken the highest for the restaurants because the restaurants have to bear two things. For example, they also have to include the cost of cooking, and they will also have to include the risk of not being able to sell. However, it is sometimes more beneficial to be in a restaurant side, because essentially in a restaurant, you are still able to deal with your mortality or to manage your mortality by cooking the crabs that are about to die first and by prioritizing sale. But in an importer or exporter role, and you do not have any cost recovery methods, for example, red meat from the crabs. Usually what happens if the crabs die at your location, you do not have any means of recovering the cost. So it is important for importers, exporters to manage mortality into a low rate and to ensure that your crabs are being turned over in a very efficient manner. For importer or exporter, you do not want to hold them for a period more than 2 to 3 days. So this is for a traditional business in which they are just buying and selling and matching the supply to the demand. The last point is that the crab market is extremely volatile. This is one of the case study we had whereby in January the price was about 34 ringgit per kilo, but once it gets to February, it can go up to about 45 ringgit or even 50 ringgit per kilo. That's about 30% to 40% increase in price just based on a variation from a different month. February is a peak period because it is usually where Chinese New Year is brought onto. So in that location, there's a very high demand for crabs, which often result in increased prices. So what are the global prices like throughout the year? In general, the first half of the year, meaning January to maybe somewhere between June, you'll see a very high price because there's Chinese New Year, there's New Year's, there's even Mother's Day. And the price will tend to drop back up during the June, August, September season, and it will slowly pick up towards year end. There are two reasons for this, mainly because of increasing demand due to first half of the year, and the second is also because of insufficient supply. So the crab market is really dependent on weather conditions. For example, if you look at the Philippine market and the Vietnamese market, what tends to happen at the end of the year is because of the monsoon season. So when you have a very high rainfall rate, what happens is the brackish water that is initially surrounding all your ponds will become what we call fresh water. And what happens is the crabs that are living in a salinity condition of let's say 25 suddenly experience fresh water of less than 5 ppt, resulting in a very, very high mortality. And that monsoon season always happens in the months of November, December. And what happens is this mortality causes a lack of supply in first half of the year, mainly January, February, March, resulting in a lack of supply and increasing prices. So the crab market is almost like stock market in which the exporter will often ask for bidding prices from different buyers across different countries, and they will often sell to the most highest price, which is very similar to what we see in a stock market. So two things you have to understand from this is that crabs are very highly perishable and their pricing is extremely volatile because due to the insufficient supply and the surge. So that's all for this lecture. In the next lecture, we will look at the profitability of the business. So we'll look at how much does it take to set up the business and what is typical operating costs, and we will give you a interactive Excel sheet for you to sort of play around and sort of understand what is your profitability like in this business. Hi guys, thanks for joining our course on mud crab vertical farming. In the previous lecture, we have looked at the different supply chain, harvest to end consumer, and the typical time it takes the crab to move from each location. In this lecture, we will now understand the typical capital expenditure and operating expenditure for running a crab farm and how to estimate your return on investment on a vertical crab farm. So the typical capital cost of setting up the crab farm will include the following items. Firstly, you need to factor in the prices of the crab houses and all of the pipings that you're going to need to connect in between all of the boxes. Thirdly, you're going to need your RAS system. So that could be your filters that is made either from a sand or a drum filter, K1 which is your biofiltration, UV will be your disinfection and any other auxiliary equipment. That will also need to include pumps and any aerators or even a protein skimmer. You would also need to perform some sort of civil work on your site to ensure that you either have a subsequent elevation for the boxes in order for the fluids to flow from the boxes into the pond. So for us, how much do we actually spend on building up this system? This is first initial capital cost details. So all of the crab house, sand filter, UV filter, pumps and piping, it was all from the Chinese manufacturer. And the price to get it onto our doorstep was about 70,000 ringgit. Note that we are working in ringgit Malaysia, so do your appropriate conversions to your individual countries. We spent about 1,000 ringgit on piping, and the K1 filter we had on our system was about 7,000 ringgit. And in total, civil works is spent about 4,000, which brings us about 82,000 ringgit. That is slightly above 20,000 US. So this is for our first try. We made some mistakes along the way. We would highly recommend to take a look at our system and see where are the areas you could typically cut costs. So in our case, we'll be running a vertical farm, but our farm is mainly used for crab fattening. So you can also do that for soft shell crab or crab fattening, or even if you would like to try out to do grow out from 100 grams or 50 grams up the way to 300 grams. So for our case, I will be presenting in this case crab fattening, and we will give you an interactive Excel sheet for you to model different objectives. So the operating costs of running a crab farm are, for example, manpower, that's first, utilities, feed, any salt. So for those who are planning to run this away from the coast, you're going to need salt to bring up the salinity of the water. So how do you get brackish water? You make salt along with fresh water to get what we call salt water. And you're going to need testing kits, and also have to include rentals and maintenance. So if you're running a crab fattening plant, so we will first start off with a few assumptions. Firstly is you're going to run about 800 crabs. Why 800? Because at times it's difficult to run up to full capacity. You're going to have some spare capacity that you might leave 1 or 2 blocks that are open, for incoming shipment. And sometimes if you feel that the first top 2 or any other case, you're not going to run at 100% capacity. So let's assume that you're going to run at 800 crabs instead of your full 1,000 crabs boxes. The fattening cycle is about 45 days with a mortality about 15%. Right now we are doing about 10 to 20%, and our fattening cycle is about 30 days. And the feed to weight ratio is about 2 to 3%. So in this case, I'm presenting a B2B. B2B is business that you are essentially selling crabs to restaurants and not to end consumer. So in a separate presentation, I'll show you what are the differences. So we know that water crabs generally retail for about 30 to 40% discount on top of the original selling price. So which gives us about a selling price of 65, and we can buy water crabs usually for 42. Note that for this case, we are actually buying it at a much lower price, and our cycle time is also faster, and our feed to weight ratio is also less, and our mortality is lower. But I'm running a conservative case, and you would see that the first thing is, if I'm running this sort of scenario, what you'll realize is the operating cost, the rental, will cost you about 450. Testing kits will make an additional 100 ringgit per month. Manpower, you'll be hiring one out of this. So one guy can run up to 2,500 boxes. That's also possible. You just have to feed every day and just clean up boxes. The next will be electricity. Water will be also another aspect to take consideration, and this is the amount of feed that you're going to need to sort of feed your 800 crabs in your system. So this is a total operating cost of about 6,300. So one thing you realize is for the revenue per cycle, it's about 25,000, which you will include selling the dead crabs for a certain price. So in Malaysia, there's a market for dead crabs. You could sell them to those who are extracting for meat, or you could either sell them to end consumers that do not mind. So the crab cost per cycle, this is what we call the cost required to buy crabs, and you will see the expenses you need is about 6,000, so which gives you about 24,000. So you realize your profit cycle is only about 500 ringgit per month, which brings us to a ROI of 200 months. So as you can see, this is very high. This takes about 10 years to break even your return on investment. So this is not likely to be viable. So what if I change now? In the previous lectures, we've also talked about economy of scale. So we've talked that 1,000 boxes might not be the most economical as you do not really have scale. So what happens if you scale up to 5,000 boxes per se? So assuming everything else is the same, I only effectively utilize 80% of my boxes. I have a mortality of 15%, cycle rate of 45 days, and a feed to weight ratio of 2%. And similarly, my cost price is 42 ringgit per kilo, and I sell them at 65 ringgit per kilo. Alright, so usually we do not only farm one sort of crab, we are splitting them out into different ranges. So what you can see generally now is the rental price of the rental will multiply by 5 times, testing kits will multiply by 5 times, and the manpower, because essentially we've mentioned early on that one person can take up to 2,500, so 2 persons effectively take up to 5,000 boxes. So essentially you are spreading out your manpower costs into 5,000 units. So electricity will multiply by 5, water will multiply by 5, salt as well, and feed. So it brings us a total of 22,000 for operating costs. So the next thing you'll see that your revenue per cycle is about 120,000, but your crab cost is only 92,000 and your expenses is only 20,000, to about 11,000 or approximately 12,000. But take note, look at your ROI. Your ROI is only 4 months, which from the original 212 months if you were to run with and without scale. So this is one of the important points I'm trying to bring out, saying that if you have scale, you're effectively spreading out your manpower costs, which brings us to reducing the amount of time needed to break even. So now it's about 52 months. Okay, so in the third case, we'll be running what we call a B2C, sort of a B2C status. So going back to the original basis of 1,000 crabs per cycle, and we are following the same rental cost, testing kits, manpower, electricity, so on and so forth. We are spending about 6,329 a month. So this is the same as the first case we presented. But what if I change my price slightly higher? Instead of 72, I'll be selling them at 80 ringgit per kilo. So this is what we call a B2C market. So one of the most beneficial point of having a RAS system which you can use for urban farming, essentially you are already closer to the consumer and you could just retail directly to the end consumer, in which they will buy crabs and cook it in their house, or even buy crabs to bring it to the restaurants. Because why do restaurants take such a high margin for crabs? Because they are bearing the risk of mortality. By moving the risk to our side, essentially we can move some of that margin onto our side, which brings us to a higher selling price. So if I were to increase, let's say on average 8 ringgit per kilo, and I look at my revenue, I've definitely increased my revenue, but while maintaining the same costs for crabs as well as monthly expense. And you can see now for every month we're making about 7 grand, which brings us to a return on investment at about 18 months, which is 1.5 years. 3 things we want to show you. The first is that having scale would help you break even faster because of the efficient spread of labor costs. And if you're not able to do that, you could probably think about doing B2C market. So B2C market is a very specific market, but however, you need to take note that for B2C, it's relatively difficult to do it at a scale size, but it is very profitable in terms of margin. So this is just 2 analysis, or what we call a sensitivity analysis between B2B and B2C. So assuming that you have 5,000 boxes, right, you're running at scale and you spend 200,000 on 5,000 boxes, meaning you're spending 40,000 for each 1,000 box, and you have a mortality rate of 12%. So you can see that you break even in about 20 months. Once you have a mortality of 15%, start increasing more than 2 years, and you have 18%, you're close to 3 years, and you have 21%, you are about 4.5 years. So what we like to show you is mortality plays a very sensitive part on your return on investment. it is actually more sensitive than capital cost. So assuming the same, look at, this is also the case for even the ROI for B2C market. So assuming that you spend 40,000 on each 1,000 boxes, you'll see that having a 21% mortality, you will still need 1 year to break even though you're serving a B2C market. So this is how different capital costs impacts your return on investment. For example, having 12% and I'm spending 40,000 on 1,000 boxes, you are spending about 8 months to break even. If I spend more on the capital cost, while keeping a mortality of 12%, I need about 10 months. If I'm spending 80,000 on the same system, I probably take about slightly 1 year and 3 months, which is 15 months altogether. So the point of this is to show you the different sensitivity for capital cost rate. Just on a glance, I would suggest that it is sometimes worthwhile to spend on a more quality system to reduce the mortality rate, as opposed to buying a cheaper system while incurring a higher mortality rate. In the next tutorial, I'll show you our interactive Excel sheet to sort of model and play around different parameters you can use and sort of try to see how does it simulate in terms of return on investment.
Hi everyone, we have shown you the capex and opex of running a vertical crab farm in the previous lecture. Today we're going to show you an interactive spreadsheet. With it, you guys can find out the returns on investment by inputting few parameters. First parameter is number of crabs. As you can see, I have made 800. It means with this 1000 box system, I will only raise 800 crabs. Next, we have cycle of days. It means the days it requires to get the crab fattened. So in this model, I input 30 days. Next, we have feed to weight ratio. It means the percentage of feed to a specific weight. Next, we have this parameter is to show you guys once you have the scalability, the ROI actually can be faster. Next, we have mortality rate. A typical mortality rate is around 15 to 25%. So in our system, the average mortality rate is 15%. Next, we have B2B sales percentage. It means the sales percentage over entire sales. This parameter will show you once you have B2C sales, the ROI can be faster. Next, we have dead crab selling price. So for some country, you may have 0, but for others, you can have $3 or even higher. It means people will buy it, cook it, and extract the meat. Next, we have crab category. In this model, I have input 300 gram category, 500 grams, and 700 grams. Units, it means how many crabs do in these systems. Basically, it's the same as the first parameter, number of crabs. So actually, it links mortality rates. And this is the average mortality rate, and this mortality rate actually links with all of these three parameters. Next, we have survival quantity. Basically, survival quantity is the unit times 1 minus mortality rate. Next, we have average size. Average size for 500 categories is 550. So H5 means start from 500 to 599 grams. So I choose the middle. Next, unit cost. It means the cost of water crab. And in our model, we assume $8.5 per kg. And I have created two selling price. One is B2B and the other one is B2C. For B2B, it will have lower revenue or lower selling price compared to B2C. For this model, it is $17.5 per kg. For B2C, it's $20 per kg. Next, we have cost. It means total number of crabs times the average size times the unit cost. It will give you the total cost of buying a water crab. Next, we have to calculate the total cost of running a cycle. First of all, we have crabs. This is the number I get from here. Next, we have to consider manpower costs. In Southeast Asia, the labor cost is around $300 per month, and we need around 1.5 people. It means we have to hire some part-time to cover over the weekend. Next, we have feed. A typical feed cost in Southeast Asia is around $1 per kg for trash fish, and for pellet feed, you can go up to $1.25. And this is higher by the crabs. So you see the formula here. It means I calculate total number of crabs times the feed to weight ratio and times 30 days. Next, we have salt cost. So somebody may draw water from the sea, and some may make seawater from artificial salt. So this is a cost. And next, we have testing kits. Testing kits to test water parameters every day, twice, and we need to include these costs in our analysis. Next, we have rental costs. So for a typical 1,000 box system, it requires 100 meters square. So you guys have to find out what is the rental cost in your country. For our case, we assume $200 per month. Next, we have electricity costs. So basically, this is the cost of per kilowatt hour, and this is the electricity consumption per month. Next, we have the water costs. So in Southeast Asia, the water cost is typically around $1 per liter. So here you have all the costs per cycle, and add up, this is the total cost per cycle. So I have I have shown you guys different percentage for each category. As you can see, the crabs, or the water crab cost usually is the highest. It's around 70%. So after costs, we come to revenue. So basically, we can create revenue by selling crabs. So I have split the revenue for two categories. One is B2B category, and the other one is B2C. So from the beginning, I choose 100% of sales from B2B. So you will not see any B2C sales here. Next, we have the revenue from selling dead crabs. As you can see, I have input $3 per kg in my model, and you can see there is revenue from selling dead crab. Okay, next we have capex. So for this model, I have assumed $15,000 to set up a 1,000 boxer system. Next, we have profit per cycle. It means the revenue minus the total cost per cycle, and it will give you the profit per cycle. So the last one will be the ROI. This number means in months. Basically, I have used this capex divided by this profit per cycle, which will give you how many months to break even this system. As you can see from this model, it takes around 10 months to break even. Okay, so now I'm going to introduce another table which will show you guys the sensitivity of different capex and different mortality. Just now you can see with $15,000 capex and mortality rate 15%, it will give you 10.14 months to break even. So from this table, you can see if you have less capex, it will shorten returns to 6.761. If you have more capex, it will increase your ROI to become 13.52 months break-evens. And if you have higher mortality rates, it will give you longer time to break-evens. So you see there is a red color here. So basically I do a conditional formatting, and for me, every investment with ROI less than 36 months is considered a good investment. So for numbers more than 36 months, actually I highlighted in red color. So you guys can play around with the mortality. So basically I can change here 15%, 20%, I can change to 30% and 40%. So now you see when the mortality rate goes beyond 40%, basically you will not get break-evens because you are losing all the money in one cycle. So let's see what is the threshold for this model. Let's see, I input 35%. 35%. You still can make money, but you will get the money back for $20,000 model. You will get in 98 months. That is not a good investment. So you can play around with mortality rates, and of course you can play around with capex. But I think the mortality rate is more sensitive compared to capex, which a typical setup cost nowadays is around $15,000. If you want to DIY yourself, you can probably go lower than that. So maybe you can achieve a $10,000 per system. So now we talk about B2B sales. So basically, let's say if I have 10% B2C sales, actually I can make my returns faster, as you can see from here. So 35% with mortality 35%, you will still see red color here. Let's see how many percent I need to convert from my B2B sales to B2C sales in order to make a 35% mortality viable. Let's see. Yeah, it turns green. So I think a 50% is good, or maybe 60%. Yeah, I think with a 50% sales revenue from B2C sale, you can actually see everything is less than 36 months. So if you have a high mortality rate, the faster ways to get back your money is to divert your sales to more B2C customer, which will give you more revenue. Next, I'm going to show you guys the system. So let's change this back to 100%. Okay, so let's see if I want to do it in scale. Let's say I do it 5,000 boxes. So it will change to 4,000 crabs in total. So everything the same. Okay, now for manpower. So usually you need around three people rotates to take care of 5 system. So let's key in 3, and the feed is automatically calculated, and we have sort. So now you have sort, we have to times 5, and testing kits you already times 5, and rental we have times 5. So yeah, everything else is properly tabulated. And the revenue, yeah, okay, so the revenue is fine, everything is calculated properly. So this capex by right should times 5. Don't worry, for this sensitivity table, it had taken care. You have times 5 system, as you can see the formula here. So before that, you can see we have red color with 35% mortality rate, and now you started to see green color for capex below $75,000. So with scale, actually you can get a faster return on investment, and because there's a fixed cost of manpower, there's a fixed cost of rental, Yep. And there's a fixed cost for testing kits. The last parameter I'm going to show. So basically, selling that crab is way to recover your losses. So let's change back everything to one system, simplify the process. And for salt is about $25 per month. So let's check. Okay, it changed. Okay, I have changed everything to every parameter to become one system. So now let's see what is the effect if I have $0 for that selling that crab. Yeah, you can see actually the ROI is longer now. By adding $1 per kg, it helps a lot. So it means if you can sell that crabs, please recover your costs. If not, you have to divert your sales to more B2C. This is the better way. For capex, you can't really reduce much. I think $10,000 is a minimum sum DIY your system. So that's it for this demo for using this interactive spreadsheet. I hope you guys enjoy. Hi everyone. From the last lecture, we have shown you the interactive spreadsheet for crab fattening scenario. Now we're going to show you another scenario, which is soft shell crabs farming. Okay, I believe you guys are familiar with this spreadsheet. So now I'm using exactly the same spreadsheet, which have a few parameters to key in. So for soft shell crabs, I'm going to emphasize on this, the number of units. So for soft shell crab, because of the loading, we can actually do up to 1,000 crabs, so we fully utilize the whole system. Next, we have cost of buying a crablet, which costs around $3 per kg, and the mortality rate is around 20% for soft shell. And this is a B2B selling price. It means $16 per kg, and the B2C selling price. So for soft shell, hardly you can have any B2C market, because but after you have volume, maybe you can try B2C, but now we just focus on B2B sales only for this case. So now, as you can see from the percentage of the cost, now manpower become, from the previous 10-15% become 51%. It is a major cost now, and the reason behind is doing soft shell crab, we have to run 3 shifts in a day. So the worker have to check every 2 hours to find is there any soft shell crab in the system, and they have to take out the crab in order to prevent the crab to become harder. Next, I have revenue. So for this average size, I change to 160 grams, and the reason behind is for a crablet is around 100 grams. So after it mold, it will have 60% increase in weight. So 100 times additional 16%, 60% will give you 160 grams. So my selling price is follow here, $16 per kg, and this is my survive quantity after I minus the mortality rates. So everything the same. If you the ROI is about 36 months, so it's still okay. I mean, it's slightly over 36 months. So from this sensitivity analysis, you can see, wow, you only have 3 green color. So yeah, now you start to see, oh, how do I have anything I can change, or how do I have faster ROI? So for soft shell crab scenario, we have to do it in scale. So let's change to 5 system, and now you see everything become green. And wait, I have to change the label. So basically I need around six person now to take care of this 5 system, and it's pretty good. Everything look better now. So doing social crab is viable. I mean, using RS vertical crab farming, but you have to do it in scale, because you have to maximize the utilization of your manpower. So that's it for today's lecture. So hope you guys enjoy. See you next time.
Hi guys, thanks again for enrolling on our course on mudcrab vertical farming. In the previous lecture, we have shown you the micro analysis of the business, meaning showing you the profitability of the business and how fast you break even for different configurations and what is the sensitivity on mortality and capital cost like. In this lecture, we will now look at the macro perspective, in which we will understand the market forces and the competition and sort of the economics behind the mudcrab business. So in the current industry, what are the current trends? In general, we see an insufficient supply of mud crabs. Secondly, we see a high demand from China, Japan, Singapore, Malaysia. We also see a dwindling supply from wild catchers, and how this export ban is going to affect some of the supplies that we see right now. And the fifth is, what are the current development on hatchery and grow out. The current major producers we have for mud crabs in the market is actually China, Philippines, and even Vietnam. So the updated figures are Vietnam. China, despite being the top producer, they are one of the lowest consumption per capita. They are only consuming about 70 grams per capita. Whereas Singapore is what we call a mature market. It's actually consuming about 1 kilo per annum per capita. So this is what we call a mature market. If China were to grow to what we call a mature market like Singapore, it will probably consume much of the seafood production all in the global market. We also start to see an increasing demand in mud crabs, mainly manifested as the Southeast Asian economy continues to sort of bloom. And this is just a snippet of one of the news that I saw on Facebook. So what actually happens is some people are actually wiring money over to, like for example, Philippines or India without having the other party, and they had no previous history in the business. So sometimes people can be so desperate for supplies they are willing to sort of wire money to someone they have never met before, and obviously the crab never actually arrived in their location. So this is what is the current status out there. We also start to see export ban. So export ban are mainly really applicable for countries like, for example, Australia, which calls for the ban for exporting mud crabs. Whereas Indonesia also started to ban crabs that are under 200 grams, and they do not allow exporting of females. So this is also true for other countries like Bangladesh or even India. That Sri Lanka also has to ban any exports that are under 300 grams. So how does this affect your business? Sometimes it can be bad news or good news, really dependent on who or which perspective you are looking at from. So if you were from a farming country like Vietnam or Philippines, if they have ongoing export ban, for example, in Indonesia or Australia, this is actually good news for you, because it means that there is a higher demand for your goods. But if you are like most of us in Malaysia that rely on the influx or import from Indonesia for crabs, you would generally find that what happens, Malaysia would then suffer from a lack of supply. And for those who are doing fattening, essentially you probably are fattening crabs that are obtained from the wild. And in this case, if you're doing that, an export ban will not help you, because you're not able to obtain or sort of import water crabs from other countries. So that is how the export ban will actually affect your business. Do spare a moment to weigh the political risk. You do not want to be expanding in a country that might soon implement an export ban. For countries like Vietnam and Philippines, it doesn't really make sense for them to implement an export ban, because they are producing in a sustainable manner. They are not relying on wild catchers to sort of to fuel for the kind of expansion. So what do we get when we see an increase in supply? mainly due to export ban, declining crab population, and we see an increase in demand consumption and a growth in Southeast Asia. We generally get what we call an increase in price. So as this happens, what we actually fear of is, will this repeat what the iron ore industry has seen, or even the oil and gas industry has seen? Because increasing prices will actually entice more people going into this business. However, mud crabs are not really like the other industry, whereby most of the tools have been formed and they just rely on increasing or what we call providing capital to expand. With mud crabs, we are still in a very early stage of the aquaculture business. We are still figuring out how to reduce mortality. So it's not likely the market is going to overheat with mud crab supply and resulting in a drop in prices. So we still see for the next 3 to 5 years, the prices will be continue to at least stay stable or further going to increase. So this is already what we have seen. The crabs are already, prices are already increasing. So this is retailing for 22 US dollar per half a kilo. So that's like 50 US dollars per kilo in Singapore, and this is about 35 US dollar per kilo, and this is about 80 US dollar per kilo. So we see that the price are actually increasing year on after year, and not to mention even festive season, you're going to see a further price hike of the nominal value above 45%. So I know that many of us have tried to use this system to achieve what we call a grow out system, but we have shown that growing out you can only realistically achieve somewhere up to 300 gram size. Anything beyond that, it will be not economical due to the molting failure process. So what are the other options you can use with this vertical farm, for example? The firstly is what we are doing, which is crab fattening. We have shown you the ROI analysis that was presented earlier. You can also do what we call soft shell crab, but you need to be mindful of your high labor costs because of the frequent monitoring of the molting status, and there are generally no post-harvest mortality if you're dealing with soft shell crab. And the third type of system, which a lot of my students or more of my clients actually integrate in, is to what we call using rust system to sort of increase the lifespan. So this is essentially being a trader while utilizing rust to maintain the shelf life of the crabs. So what's the pros and cons of each of this business? So if you're doing crab fattening, I would say crab fattening still remains one of the most profitable and underexplored business model in mud crab farming business. However, your cons, you really need to know what you are doing in terms of technical risk, and you need to make sure that you are familiar with your suppliers, logistical, and you also understand in-depth understanding of the rust system. So however, you need to take note that sometimes the availability of water crab is not constant. You have a lot of supplier risk in terms of, essentially, if you're going to spend X amount of money building your facilities, the supplier can decide to raise your price, and there's nothing really much you can do about it unless you buy from multiple suppliers. So that's what we call high supplier risk. Your competition will still be mainly from wild catchers, and you need to compete with them in terms of price, but it's still likely that your fattened crabs are still as of a better quality as of the mud crabs that are taken from the wild and passing along the supply chain. Soft shell crab system, on the other hand, you generally get less competition because you can't really harvest soft shell crab from the wild, and there's also no post-harvest mortality. However, you need to understand that you need what we call economy, or so you're going to need 3 to 4 workers and at least 5,000 units to be economical. However, the demand for soft shell crab is slightly lower than the live crab market. You're looking at specifically Japanese restaurant or some specific restaurant. And in order to be economical, you usually need to be located a huge crablet source, or you are located beside a hatchery that could consistently provide you with crablets, because if you're running soft shell crab, you're going to run at a very high volume. Your competition in this soft shell crab business is likely to be bigger groups. For example, since everybody knows that for soft shell crab you require economy or scale, so usually what you'll see that your competition are usually big groups that have invested huge amount of money to be in this business. So retaliation is likely to be stronger, and they are likely to retaliate in a more defensive manner. For example, if you were to drop the price by 1 ringgit per kilo, they are likely to drop 2 just to outcompete you the market and re-raise price once you're gone. So most of the soft shell crab producers in Malaysia uses the cage and this is popular in India and Bangladesh as well, that uses tide for water change. So soft shell crabs that are produced from RAS system have known to be better tasting due to the lower ammonia in the water. So it's really up to you to sort of try to find the correct market demand for your soft shell crabs that are produced with RAS systems. The third is to utilize RAS system as a form of life support. So one of the pros is being really extend the shelf life of your crab and really reduces the risk of trading. Please note that one of the mud, even if you're in from a perspective of a trader, trading mud crabs is very risky as well, because mud crabs are highly perishable. You can utilize the full capability of RAS being based away from the coast, and you can be really close to the consumer. And most importantly, you are able to sort of guarantee price stability. What do we mean by price stability? You can sometimes hold crabs up to 2 weeks, or sometimes even for a month. So what you could do is to purchase the crabs during excess supply and sort of match the excess supply to where you have high demand but no supply. So it also gives you the ability to access B2C market, because traditionally traders do not enter the B2C market is because the B2C has a lower volume and nobody really wants to hold so much of crabs. What are the cons? One of the biggest cons of running your RAS system and using it as a trading system is due to the influx of crabs. Usually you get a lot of diseases in running your RAS systems, which is really hard to control. Generally, your competitors might be seafood traders that do not really have a holding facility. What they use is what we call a just-in-time inventory, and generally what they do is they'll take order 2 days to 3 days before the weekend, and they'll order it from another country, import it and redistribute. Nobody really accumulate inventory, so what happens if the price increases? They would generally just stop trading. We're going to show you a quick video of the lobster industry, and you can see from this video that how RAS is applied to serve what we call a B2C market, and you can also see the rise of China and a lot of common topics that we have been talking about. So the lobster industry is more advanced than the crab industry.
It's a classic story of Atlantic Canadian success. The company started back in 1976 with two brothers-in-law, John Risley and Colin MacDonald. They started buying lobsters here in Nova Scotia and bringing them down to market in Boston. Clearwater is dedicated to sustainable seafood excellence. This company is about responsible harvesting premium quality shellfish and bringing that quality shelf to our global customers.
There's some products that are very unique to our marketplace. One of them that we sell is the Arctic surf clam, otherwise known as beiji bei in China, used in sushi and sashimi dishes as well as numerous cold salads.
The Chinese consumer demand for Canadian seafood products.
The Arctic surf clam, otherwise known as beiji bei in China, used in sushi and sashimi dishes as well as numerous cold salads.
The Chinese consumer demand for Canadian seafood products is unprecedented. Canadian lobsters are actually fished during the time of year when they're in their premium quality state. And then the dryland pound chills the lobsters to a winter state. So we can supply the Chinese market with lobsters as if they were plucked out of the ocean during the time of year when they are fully meated and hard shell.
What's exciting about Clearwater expanding in China is the size of the opportunity, the growth of the emerging middle class, and the rapid change of consumer buying.
Already that country, given their population base, eats the most seafood in the world. They already account for over 35% of the world's consumption of seafood, and that's projected to grow by almost 10% over the next 5 years. Tmall is an opportunity that came to Clearwater Seafoods. We've historically been a business-to-business focused company selling our products to restaurants and food service establishments around the world.
Being on Tmall, we're reaching customers today that we haven't reached before. Within a few minutes, you can order something and get it at your door. I never thought that would happen in frozen seafood.
The Tmall flagship store is important to us because it gives us a platform to highlight our products, but also tell the story behind the products. It's there that we can talk to consumers about how we sustainably harvest the resource, that it comes from the fresh waters of the North Atlantic, that we do everything on board the vessels to keep the product quality at its highest state until it's eaten by consumers when it gets to China. Tmall's been a great partner for that, and we're looking forward to growing with them in the future.
So lastly, I want to then emphasize again the possibility of using a RAS system to serve the B2C market. So as we can see in the earlier video, that the vertical farm really enhances the retail experience, and you're able to fulfill what we call low quantity purchase and charge at premium, essentially towards your side. And how do you mitigate that risk? Using RAS systems. So apart from the general B2B business, how do you target the B2C business? One of the best ways is what we call social media. So this is some of the cases that we have run that bring in a lot of ROI in terms of marketing on Facebook. So if you're trying to sell clothes or some other accessory on Facebook, it remains very competitive because a lot of people are doing it. But if you're trying to sell crabs and consumers, there are not a lot of people who's trying to do this, and generally Facebook would not charge you a very high cost in terms of marketing fee. So that's all for this chapter. In the next chapter, we will conclude some of the other future developments and show you what are the areas of potential that you can possibly look into.